Welcome, everyone. We're so excited to have you with us virtually this year. Last year, the Chicago Robotics Alliance, which is a network of a bunch of Chicago FRC teams, hosted the first CRA conference at Lindblom High School, thanks to 1781 Electric Eagles for hosting us. We quickly realized it was an incredible opportunity to exchange knowledge and build our FRC community. However, with the risk of COVID-19 this year, we didn't know how to achieve the same results.
All right, so we know that last year was pretty disappointing, and ended in a way that many students were very disappointed. Mentors, all of the community was definitely had a hard time. But you know, it not being able to attend as the competitions expected and so on. But what has been really wonderful is seeing the ways in which so many teams have continued to develop and reach out and work to get better with despite all of the adversity that's gone on. And so really what we wanted to do with this stream is figure out a way to continue to augment what we've been doing with the other teams and to help everybody share out. So we've got a whole bunch of people here today to kind of come together and still be able to connect for across digital barriers and through physical barriers and so on. So we're really looking forward to it.
So the 2020 CRA Conference is a result of trying to keep us together. We got some amazing students and mentors that stepped up to share their knowledge with all of us. We got 15 different sessions from 6 teams and the first Illinois Robotics Alumni Group, covering things like student leadership to design process to programming. Our goal today is for you to leave with having learned something, to reconnect with the FRC community and keep your minds churning. We hope you experience, or this is an experience that'll add to your journey of being on a first robotics competition team. So thanks for joining us.
So really quickly, we wanted to go through an overview of the CRA conference document, which you can access by going to this bit.ly link, bit.ly/2020 CRA conference. This document is comprehensive and will go through all of the different things that you need for today. This is what you should be saying when you reach this page. At the very top is a table of contents that will allow you to jump to the various sections, especially the descriptions of each session. The first section is a link to all of the streams over here, which are all on YouTube. The second section shows you a comprehensive schedule. You can see the stream link at the very top. The closing and the closing remarks and the intro remarks will be cast on all of the streams. And scrolling down are the descriptions of each of the different sessions that you can read about and check out. Lastly, as you watch any of our streams, you'll notice that we've enabled YouTube live chat. So if you need to ask any questions, you can feel free to do it through that. We'll be monitoring that chat and passing on the questions if we have time to our presenters. There is going to be a 10 to 20 second delay, so be patient with us. This is also our first time doing this stream. As many of you know, we're very good at building robots as mentors, well, some of us. So this is new to all of us, but we hope that you guys enjoy this experience. We know a lot of you have tons of questions about the upcoming season and what's happening here in Illinois. So it's my pleasure to introduce Dan Green and invite him, the Executive Director of First Illinois Robotics, to provide you with what's happening this year in the state.
All right. Hello, everybody. I wish I could be looking you in the eye, but I'm looking in a computer. That's the way it goes. I hope you're all doing well and surviving this in this crazy time. Truly, this is my 26th year as being part of First, and every year is a little different. And I don't think I have to tell anybody that's watching this that this year is definitely a little bit different, maybe a lot bit different. Um, so welcome to it. I'll give you a little bit of an overview of some of the stuff going on at the first level. As you know, we've got all different programs, and all of them have been virtual to this time. Whether it's the younger programs where we've got the first Lego League or the first Lego League Explore or the first Tech Challenge or whatever, it's all virtual so far. We're hoping that we can do some stuff in person for some of those programs after the new year. We have to evaluate and see where we are. Um, but if we can safely do it, we will. It's not looking great that that's going to happen, but that doesn't mean we're not going to be evaluating it and hoping we can do it. Um, um, as far as FRC goes, as you know, we've set it up to be virtual this year, and we've come up with 3 different challenges, and I'm sure you're going to hear more about them today. But real briefly, I'll just at a very high level mention them. As you know, we've got a skills challenge where you're actually going to be able to show how well your robots can do some of the challenges that are associated with this year's game, which, as you know, is also a repeat of last year's game. Also, there's a challenge associated with creating a new competition, which is actually pretty exciting because I think the inputs that we get from all of you as far as different games and potential games, people at headquarters are going to look at that, and I will not be surprised to see a lot of the inputs that we get from the different teams helping to form the new games of the future. So that's kind of exciting. And the third thing is solving a real problem, the innovation challenge, similar to what's been done in First Lego League for years. A lot of us have always thought, well, that's one of the best things that we do in First Lego League. Why don't we do that in the other programs as well and give the older students an opportunity to look at a real world problem and come up with some solutions for it? And so that's the third part. That's part of the virtual challenges. The other thing that I want to just remind everybody of is some of the traditional awards that are given out. For example, the Woody Flowers Award, the Chairman's Award, the Dean's List Award. Those are going to also still be judged this year as usual. So please submit those and do that as you would. One of the things we've changed in Illinois is we usually have 2 different regionals. We have the Midwest Regional in Chicago and the Central Illinois Regional in Peoria. This year, we're combining all of Illinois into one event, one virtual event. So it's just the Illinois event. So we're accommodating by doing the judging a little differently, but we're combining it all. If you have any questions, you can always reach out for me. And Sravan, I think you're going to put up my email address so people can see it if they want to reach out. If not, I don't see it, but maybe that doesn't mean it's not up. It's dgreen@firstinspires.org. You can reach out to me, and if you got any questions, I'd be happy to do my best to answer it. But the thing that I really want to mention to everybody is even I know this is a difficult time. It's difficult for all of us, young, old, and in between. It's just craziness. But stay inspired. The fact that you're involved in something like this is great because hopefully it'll be an opportunity, at least virtually, to connect with some of your cohorts and stay excited about things. Um, I've always been impressed with our participants in these programs. The FRC level, of course, you guys are great, and I'm sure that even under these difficult times, it's still been impressive. The things that I've heard that different teams are doing, some of them, it's just amazing. Some of you I know are just struggling to stay above water, and that's amazing as well. So just whatever you're doing, keep it up. The other thing I will ask is, um, as you're out there, there are a lot of people that are less fortunate than us and are having a lot of problems, whether it's physical, with health, with anything. I mean, I know people have lost people that are very close to them, and that's terrible. I have as well, and it's very difficult. But if you see somebody that is struggling and needs some help, reach out and try to help them. If you have the ability to do it, try to do it. Um, um, one of the things about FIRST and the people that participate in FIRST that has always been so impressive is the character of the people that are involved. And it's always something that it's one of the things I'm probably most proud of participating with the group of people that I participate with. And all of you are a definite part of it. I've always been so proud of that. And, if you think you can get out there and make a difference, do it. I mean, just take it upon yourself and do it. If you need help, don't be shy about asking for help. People in FIRST are a close knit group, and there will be people that are willing to help. But like I said, try to stay inspired. Um, by us being inspired and us having energy, it helps. It's contagious, and it helps other people that might need it. So keep that in mind. I hope you all, stay excited. And most importantly, I hope you all stay safe and healthy. And good luck. And I'm excited about this day, and I hope it's a great one for you. So thanks, Robin, Mike, Nick, Lindsay. You guys are great.
Thank you, Dan. Appreciate it. Well, everyone, we're going to be back with our first sessions in about 10, 15 minutes. So check back in 10, 15 minutes, and you'll hear from our first presenters. Thank you guys again for joining. See you soon.
Hi, everybody. This will be an introduction to FRC electronics. I'm really happy to be presenting at this conference. It's an honor. I'm glad that I get to spread what I know. This year will be especially hard to spread information to incoming members, and once all the seniors leave, I want to make sure that everyone has all the resources they need. So I think this is a really good conference, and I'm really happy that Chicago Robotics Association is allowing us to do this. So in this presentation, I will cover the most common control components for an FRC robot, as well as personal team preferences. I will also include tips to help maintain wire management in a progressive learning environment for new members. Some of the electronics components that I will be covering today include the battery, a 20 amp circuit breaker, the Robo Rio, the PDP, the VRM, the PCM, various motor controllers, and the radio. If you have any questions during this presentation, there will be an opportunity when I'm finished to ask them. And if you're unable to ask, you can email frcteam4645@gmail.com. So let's begin. Again, if you have any questions, type them in the chat in the YouTube Live, and I will try to answer them at the end. Hello, my name is Cassie. I am the electronics sub-team lead for the Chicago Style Bot Dogs, Team 4645, and you can contact me at frcteam4645@gmail.com. What better way than to start with a quote from Woody Flowers? Gracious professionalism, meaningful life, satisfaction, happiness, joy, and fun. Some things to remember during this presentation. Every team has a different preference of which electrical components they use. If your team uses something different, that is totally fine. There will be a more extensive presentation on electronics directly after mine by Ron Faulkner. And this is a lot of information in a little amount of time, so please bear with me. Starting it off strong with the battery. The battery for an FRC robot should be a 12-volt DC battery that runs at 18 amp hours. The batteries used for FRC are sealed lead acid batteries that are able to keep up with the high current demands of an FRC robot. All components of the robot are supplied power from the battery. Some tips when receiving new batteries or even keeping up with older batteries is to get a battery tester. My team last year got the battery beak, and we brought it with us to competitions and used it in the lab to make sure all of our batteries were working well. By consistently checking batteries to optimize the electronic system, another thing to check is that the connections on the positive and negative terminals of the battery are always strong, secure, and covered. The circuit breaker. So the circuit breaker is 120 amps. The circuit breaker is a safety measure that ensures the battery never supplies more than 120 amps to the electronics board at a given time. It acts as the main robot power switch, and its basic function is to interrupt current flow after a fault is detected. It works by monitoring the current coming from the battery, and if there's ever more than 150 amps, which is surprising because it says 120 amps, but that's not true, it then pops open, cutting off power to the entire robot. It is connected directly to the battery and then to the PDP, and it's a quick way to shut off all power to the system without having to unplug the battery all the time. The Robo Rio. The Robo Rio is the brain of any FRC robot. Its main function is to receive information from the computer via USB or Ethernet cable. It connects to the designated 12-volt port on the PDP. There are different ports on the Robo Rio that allow various components to be controlled at one time. This includes motor controllers, sensors, the signal light, etc. One thing to be cautious of when running many components at a time is brownouts. Brownouts are caused when there is too much current draw from the various components. To avoid this, your team should make a power budget of the maximum current pull from each component you plan on using. And the good thing about this is once you have all the data for that compiled, you can use it year to year. The PDP is short for the power distribution panel. This connects it's the battery and then the circuit breaker connected to the power distribution panel. The PDP is used to evenly distribute power to all components on the electronics board. It is connected to the battery through the circuit breaker. It includes ports for the motor controllers as well as other outputs for various components on the board. It has a CAN wire port with a termination resistor that can be switched on or off to end a CAN daisy chain. In the middle of the PDP, there are snap action slots for circuit breakers ranging from 20 to 40 amps depending on the port and the component being inserted into the corresponding port on the PDP. I like this image because it shows you all the different ports. So up here you can see, oh, you can't see my pointer. That's all right. But there's VRM ports, PCM ports, and then the ports along the red and black things that are parallel are for the motor controllers mainly. Moving on to the VRM, the voltage regulator module. The VRM acts like an extension of the PDP, where it supplies power to certain components. It regulates the voltage coming from the battery through the PDP to power smaller components. It has ports for 12-volt and 5-volt outputs, also allowing different amperes of current from 2 amps to 500 milliamps. Suitable for components such as the robot's radio, custom circuits, IP vision cameras, etc. The VRM receives power from the battery through the 12-volt input port at the end of the component that is connected to the PDP at the specified VRM output port. There's also signal lights on here to show whether each port is working correctly and supplying power to the various components. The PCM is the Pneumatics control module. The PCM is connected to the PDP by the PCM ports at the end of the PDP and wired to the 12-volt input on the PCM. It has 12 volts or 24-volt outputs that power the pneumatic solenoids and the compressor. The PCM receives commands from the RoboRio via CAN wires and sends that information to the compressor. The component also has an input for a pressure switch and will collect information on the solenoid states, pressure switch states, and compressor state. In the middle of the component, there are also LEDs that provide insight to the status of both the CAN and the individual solenoid channels. And if you want to learn more about pneumatics, there's a presentation by Natalie later on today from my team. Motor controllers. This is where electronics kind of branch out. So every team has a different preference of which motor controllers they like. There's various different brands, and within the brands, there's various different versions. My team personally uses Talons, and we usually use the Talon SRXs, but other teams that use different motors, such as the Falcon and the Neo motors, use different motor controllers for those specific motors. So if I don't cover the motor controller that your team uses, that is totally fine. I just picked out 3 of the main variety. Starting it off with the one that my team personally uses, we use the Talon SRXs. So the Talon SRX can be controlled over the CAN bus or PWM interface. When using the CAN bus control, this device can take inputs from limit switches and potentiometers, encoders, or similar sensors in order to perform advanced controlling, such as limiting or PID closed-loop control on the device. The Spark Max can control either traditional or brush DC motors or Rev Robotics Neo brushless motors. It can be controlled over the PWM, CAN, or USB for testing. The controller has a data port for sensor input and is capable of closed-loop control modes when controlled over CAN or USB. Then there is the Victor SPX. My team uses a few of these as well. The Victor SPX motor controller is a CAN or PWM controlled motor controller. The device allows for an easy connection to the RoboRio PWM connectors or the CAN bus chain. When controlled over the CAN bus, the device has a number of closed-loop features also present in the Talon SRXs. So these are what the motor controllers look like. The Talon SRX on the left, the Spark Max in the middle, and the Victor SPX on the right. So this is talking a little bit more about the motors that each motor controller works with. Some work with multiple types of motors, and these are the main types of motors you will see being used in FRC. The motor controller you choose depends on what motor your team plans on using for the robot. There are some motors that don't even need a motor controller, and I will cover that, and some that require specific to function properly. All motors are supplied their power through the channels on the PDP as stated earlier. So starting it off with the motor that my team started using last year, I think it came out last year, is the Falcon 500. The Falcon 500 is powered by an internal Talon FX, which is a built-in motor controller. So this is one of the examples where you would not need an external motor controller. This means, it can be directly added to the CAN daisy chain, and it saves a lot of space on the electronics board. It is designed to increase power and efficiency while reducing size and weight. That's how they designed it. Now for another popular motor is the Neo motors. It's the Neo brushless motor. The Neo is very compact and lightweight, yet still very powerful. Something to consider is that brushless motors like the Neo can only be driven using brushless motor controllers, and it will be damaged if you use the wrong motor controller for it. Currently, the only FRC legal brushless motor controller is the Spark Max, as mentioned on the previous slide. The most common motor is the standard SIM motor. The SIM motor is one of the most common motors in FRC. It can be used to power a drivetrain or other large mechanisms. It works well with the various Talon and Victor motor controllers, but it will also work with the Spark Max. So again, when choosing your motor controller, you really need to talk to your other sub-teams to figure out what motor controller would be best for the motors that they're planning to use and everyone else on the team is planning to use. Now for the open mesh radio. So the radio is used to provide wireless communication to the robot. You can use it both wirelessly or even connect to the robot through an Ethernet cable. The radio is powered by a 12-volt 2-amp output on the VRM and is connected to the RoboRio via the Ethernet cable. There are two variations of the radio. There's the OM5P-AN and the OM5P-AC. They pretty much look the same. They have the same function. The only difference is that the AC is newer than the AN and has slightly more ventilation. One thing to be sure of is that the radio is able to connect to the computer that you're planning to use during matches or during practice and continue to stay connected throughout the match. So one thing to help with that is test different places to mount your radio so that you can always get a really good connection, because the worst thing is if you lose connection with the radio during a match. I'm going really fast. I'm so sorry, guys. So I did not make this diagram. I wish I did. Another team made this diagram, but it basically puts together all the different components. If you were able to see my mouse, which I don't think you are, you can see all the different connections, the different gauges of wire that you should use for each one, and the route that the CAN wire takes. So one thing to consider is there is the CAN wire termination port, but if you aren't using that, your team will need to have other generic electronic supplies such as resistors to be able to end off that CAN daisy chain. So yeah, this diagram is very helpful It shows basically the entire electronics board with up-to-date components. So yeah, if you ever need help wiring, I would reference a diagram similar, or you can make your own. So now I am done covering the main FRC components. I will now move on to talk about wiring and board design tips that my team uses. Throughout the years, it's very helpful. We've gathered a lot of information. We figured out what materials we like and what we don't like, what connections we like and don't like. And it's always constantly a lot of testing and planning every single year. You never just dive right into making your finished electronics board. You always want to plan it out, make it in CAD, test out different wire connections that you like. And I will get a little more into that and show you what we've learned. So my favorite connection and my team's favorite connection, well, I'm speaking for my team right now, but I'm going to assume that it's their favorite because I like it, is the NASA Splice. So my team calls this the NASA Splice because it's the same connection that NASA requires for all of their connections. This splice provides a very strong connection and is extremely streamlined, which allows for clean wires and easier wire management. I use this splice mainly for CAN wires, but it can also be used for other connections, especially for a wire extension. So if you have a wire that is too short and you need to add on to it, you can get a scrap piece that is the same gauge and use this splice to make a good connection. Even though they are very strong connections on their own, every single connection should always be finished with solder and re-insulated with either electrical tape or heat shrink tubing. Yeah, my team's main use for this is for CAN wires because the daisy chain can get a little messy, and if you have one break in your daisy chain, none of your motors will run and none of your components will properly get the data that they need. So we like using this splice because it's pretty foolproof once you take the time to do it. It's very, very strong, so you can pull on it and tug on it without it breaking, especially if you solder it. And it has a lot of different uses. And it just makes your wires look nice because it's very thin, the connection. So here's a different type of connection. These are just a kit of various wire connectors that your team could get and should get. So the thing I like about this is there are so many different connector pieces and you can buy them in very large assortments for pretty cheap. I recommend getting a kit like this one, pictured right, and testing out which connections your team likes best or which connections you end up using the most. Anytime you use a connector piece, you should always make sure that the wire has a good connection with the internal metal piece so that it's clamped down hard enough so that the wire will not come out of the connector. The downside to these connections is that they tend to not be very strong and do not guarantee a proper connection. It's very easy to not get a good connection between two wires with these, but they're pretty simple to use. You kind of just stick them on and clamp them down. There's some other types of connections that require specific crimps and clamps. But these are some of the main ones that you can get in a big variety pack. And I recommend all members just testing them out, seeing what different connections you use, where you like to use them. Last year, my team ordered 1 million different connections from like China. And we just like a whole bunch of cool ones like 90-degree connections, 3-wire connections, a whole bunch of different stuff. And it's just kind of fun to play around and see if there's a new connection that you discover that you like. Ferro wires. So ferro wire crimps is an end connector for wires. I love these things. These things are great. It covers all the loose strands of copper wires while still allowing a proper connection. It's especially helpful for really small small wires for inputs and outputs on various components like the PCM and VRM. Because you don't have to fuss with the stray wire strands that could possibly cause a short, It's also handy if you plan on rearranging or removing wires multiple times because it prevents breakage at the ends of wires and protects your components from small copper pieces being lodged into the terminals. So nothing's worse than trying to fit a wire of any gauge into a port and all the strands fray out. This kind of prevents that. It does prevent that. You could buy a large kit of these as well. Each color goes to a specific gauge, and you do need a special crimp for this, but they're really fun. They kind of crimp it by squeezing all the edges so it's evenly crimped all the way around. And the good thing about these connections is you won't have to keep cutting your wire shorter and shorter and shorter because it will preserve the end of it. So I think this is a necessity for all teams because we love them so much. This one is a cool one. This one we discovered last year. This is polycarbonate sheets, or in other terms, corrugated roofing plastic. That's kind of the for sale term. So before discovering this material, thanks to the Lindblom Electric Eagles last year for showing us this material, we were using heavy perforated polypropylene sheets, which worked well for our robot, but you want to cut out weight wherever you can, and those ended up just being way too heavy, even though they were perforated. So this material is extremely rigid and very light. Since it's composed of hollow cells and it's very easy to drill into and attach components and wires to the board, my team really likes using zip ties, so you can easily poke holes in this thin plastic and loop your zip ties through it, secure stuff down. Or I know there's other wire connections that you can connect to a board, like Velcro or stick on like clamps. I don't have a picture. I'm sorry, guys. But yes, the cool thing about these that I discovered while making this presentation is that they come in different colors and they are extremely cheap. So I wish that my team could have used a different color last year because it would have been really cool because we wanted to incorporate LEDs on our robot if we had enough time after our first competition. So I think a lot of teams will be starting to pick up this material because it's very easy to cut, it's very strong, and it's very light. So I definitely think you guys should think about using this. So I kind of ran through that very fast, so there will be a lot of time for questions. So that's basically all for it. I can keep blabbing on, but I'd like to answer some questions that you guys have. And if you are unable to get your question answered, again, you can email me. Before we get into questions, I'd like to go through my acknowledgements. Special thanks to my team members and coaches who have supported me and taught me everything I know. I love you, Elizabeth and Ghost. You taught me all the electronics I ever need. I'm so grateful for the Chicago Robotics Association and the ability for Chicago teams to work together through a progressive learning environment, and for allowing me to present and share what I have learned with the rest of my community, because sending out information is so hard right now. So I'm glad that there's some way that we can still have our community come together through the Chicago Robotics Association. So if you have any comments, please put them in the chat and the YouTube live, and my coach, Miss Vetvic, will hopefully read them off to me because I'm not on the live.
All right, Cassie, thank you so much for sharing that with us. That was a fantastic presentation. Just double checking, you can hear me, right?
Yes.
All right, cool. So I'm monitoring our chat so far, and we've got a lot of love for the polycarb. So it looks like teams are using that and enjoying that. So we've got a couple questions that are coming through. It looks like Sharik Siddiqui. I apologize if I get your names wrong. I'm going to do my best. But this team member is asking about going more in depth about the electrical budget. So can you talk a little bit more about some of the parts that we use and possibly what those costs might be and how we fundraise and cover those costs.
Yes, so I personally was not in charge of the electronics budget last year, but we usually have a team spreadsheet that we split off into each sub-team, and on those, we write down the cost. We have a document with the cost of every single component that we use, and then we are able to reference that when using our electronic budget sheet. And sorry, my cat is wanting to make an introduction. But yes, so then we reference that. We look at how many components we use, and we multiply it by that number to get the total cost for that component. We add them together, and if we need to cut down something, we usually end up taking out a motor somewhere or a motor controller. Last year, since we were using the Falcons, we were able to take off a few of our extra Talon SRX motor controllers, which cut down on weight, and it also allowed a lot more room for our electronics board, which was very exciting. Yeah, so that's our main way of keeping track of everything and knowing how much budget we have for each component. There's also a lot of places. Yeah, that's basically all I have.
Sure.
For that question.
Yeah, thank you. No, thank you for sharing. Yeah, I can speak a little bit to this as well. So our Team 4645 is really student run, and a lot of our students do the research on what components that they would like to incorporate in their designs, and then they look up where those parts are available, whether or not those parts are available from vendors from Chicago Public Schools, and they make requests through a Google form to have those components ordered. One of our biggest vendors for that we use here in at Team 4645 is McMaster. We order a lot from McMaster, and a lot of our electrical components, Cassie, correct me if I'm wrong, are from Andy Mark too. We get a lot of the pre-assembled kits that, like you were talking about, with each of the variety of components. So feel free to continue dropping questions in the chat. We're monitoring that here. It looks like that was really the only one that came through the at first, but I've got a couple for you, Cassie, if you don't mind me putting you on the spot. So it's going to be more about your experience as a student of FRC and a team member on Team 4645. And so I know that something that we're missing is just the camaraderie that we feel in the community that we feel when we're at competition or in the build season. So would you share one of your favorite memories about being on a team like an FRC team and why it's important to you?
So my favorite, so I joined the robotics team my sophomore year of high school. And so last year I was the second lead of electronics. And the main purpose of our second lead of electronics is to make everyone feel welcomed and to make everyone know that they're an important aspect to our team. So last year I had to do a lot of thinking about how I can incorporate everyone and make them, even though we have a large team of 100 plus members every year, it's hard to make everyone, not everyone's allowed to actually work on our robot, our competition robot. So we need to find different ways to make everyone feel involved in the community. So probably my favorite memory is we would always have meetings. I'd run the electronics sub-team meeting, and then in the same room on the other side of the room would be the programming meetings. And we're supposed to be working together, but it was always hard for us to actually plan something out or get something where we'd learn a little bit about each other's things. But it was nice to be able to make the test boards for them, give them to them, walk around, and teach the team members how to troubleshoot their practice boards, which is what we'd make for the programmers. And one way that we had a kind of team bonding is last year we hosted a little holiday party instead of our team meeting. And we had a whole bunch of alumni come by, and it was so nice to see old team members that had graduated, and all the new members got to talk to their friends that were in programming that they didn't get to talk to during the meetings. And it was just a lot of fun. I think it's really important for us to make sure our sub teams talk to each other, which is especially hard this year because we're in separate Google Meets on separate days. But if you can, try to get everyone to know each other on your team and do little fun activities that aren't robotics related, where you can just get to know each other and make memories, because that's the best part about FRC, I think.
So you spoke a little bit about the communication among sub-teams. Can you talk how important the relationship between the electronic sub-team is and the programming sub-team?
Yes. So other teams might not have this problem because you might only have a few people that run between sub-teams. But for us, there are two totally different sub-teams, and I wish I knew more about programming, and programming wishes they knew more about electronics. The reason behind that is they work hand in hand. If there's a problem with the robot, it's always an argument between whether it's an electronics problem or a programmer's problem. And it's kind of a running joke we have that it's both of our like it's always one of us that made the mistake. So that's why we need to work together, because if we're not working together, we'll have problems and then we'll both have to solve them separately. But if we know a little bit about each person's sub team, we can also help them figure out what the problem is, because we know our stuff's working and we can help look through their stuff, there as in programmers, to see if maybe it's something on their side. The way that we kind of work together best is last year we created a troubleshooting document where we have a list of certain things that we run through if there's a problem. So there's certain things that we test first. Like the first one would probably be like check the CAN wires, make sure they're all good. And then programmers each have their own troubleshooting guidelines as well. Yeah, it's just really important to know about each sub team a little bit so you can work better with them as a united force and not individual separate groups, because you can't have a robot without electronics, but you also can't have a robot without programming and fabrication and the drivetrain and the CAD team and all the different people that need to come together to make a robot the best that it can be. So I think it's really important to try to talk with everyone and learn a little bit of everything while you have the chance to.
Absolutely. Well, I have one last question for you. So just to encourage everyone out there who might be listening in on the live stream for stream number 3, if you've got a question, feel free to drop it in the chat. I'll pass it along to Cassie. And of course, at the beginning of this presentation, we mentioned that, and even on the slide that Cassie's projecting right now, we have our team email. So we would be more than happy to address any questions that come in after the stream ends or the session ends. But Cassie, I do have one last question before we transition to our waiting page. So what's the most important lesson that you've learned by participating in FRC? So it doesn't have to be about electronics. It doesn't have to be about robots or engineering in general, but in overall, being part of this program, FRC, what have you learned that is most important? I'll give you a moment to think about it.
So last year, this is kind of a story, but I'll get into it. So last year we got our new Falcon motors, and because of that, we had to undo all of our CAN and redo it, which is kind of a pain because there's so many little wires and you don't want to accidentally, each time you solder them, if you undo it, you have to cut off more length of the wire. So they end up getting pretty short pretty quickly if you keep having to redo them. So it was just a lot of back and forth, a lot of switching out different components and having to redo wiring and the wires getting shorter on all the components. So the main lesson that I have learned is basically to go through the engineering process. So you need to plan it out, and then you need to basically do it right the first time. So, and if you don't, then you just have to do it again, and not get discouraged with that, because last year I would say we had to rewire our CAN wires through our robot maybe 5 times within a span of 2 meetings, which was kind of stressful because it was the day before competition as well. So we always get our electronics board done pretty fast, and then we have to pass it over to programmers to program, and then they pass it over to fabrication and design, and they have to put it onto the robot and start driving it around and testing it out. So the main thing is do it well. And if you have any questions, ask, because you don't want to do it wrong and have to start over or accidentally break something or mess something up. The robotics community and the FRC community is so accepting and so willing to teach you things that without asking questions, you won't learn anything and you won't grow bonds with people by them teaching you things. So the main thing is just, if you're ever not sure about something, ask a question. And before you do anything, make sure you know you're going to do it right, so that you can have maximum efficiency and effectiveness and just have a good robot, hopefully.
Fantastic.
Yeah.
Well, thank you, Cassie. Thank you so much for sharing all that you've learned throughout the time that you've been a team member on Team 4645. No other questions came through the chat. So again, I'm just going to remind streamers that they're more than welcome to continue to drop questions in the chat, or to reach out to us at frcteam4645@gmail.com. We're going to take a short break, and we'll be back at 3 o'clock with Ron Faulkner, who is part of Team 2451. He's going to present a little bit more information, a deeper dive into the electronics that Cassie introduced here. So we'll see you again at 3 o'clock. Cassie, thank you for all of your work on our team and for putting together this presentation. And everyone who is watching out there, we will be back at 3 o'clock. All right, thank you.
Thank you. Thank you for letting me present to you guys.
All right, everyone. Welcome back to Stream 3. We are going to get started at 3 o'clock with Ron Faulkner, who's a mentor from Team 2451. He has been with the team, Team Pawnage, for 11 years. He's an electrical engineer, and he has his bachelor's in electrical engineering and his master's in computer science. So he's going to be expanding upon Cassie's presentation with electronics. He's going to go into a much deeper dive into the specs, all the technical documents, and just the technical information that you'll need to know for electronics in FRC. So in just a moment, Ron will join us. Enjoy.
Good afternoon, FRC teams. Welcome to a deeper dive into FRC electronics. I want to let you know I have a lot of slides here, and there's a lot of information. So don't try to completely understand everything that I'm going to present here, but just see it as, oh, we need to look at this, or this is an interesting item. Our team needs to do some more research. With that, I'm going to dive straight in. So if you're going to do electrical engineering or you're going to do robotics, you need to understand the fundamental laws that surround it. We deal with power, which we do in watts. We do amps, which we do current as we do in amps. We do volts and volts, and that's the power behind it. And we do resistance in ohms. And these four things is what rules the electrical world. And you have to understand the relation. All these formulas here, you don't need to know them all, because when you boil it down, these are the four that I use. Voltage is current times resistance. Current is voltage divided by resistance. Resistance is voltage divided by current. And power is current times voltage. And that is how I think of it. And then you can derive all the others from these. So one of the things to understand electrical is the water tower analogy. People don't understand what is current, what is voltage, what is resistance. So we use a water tower analogy. So the weight of the water up here in the tower is going to be your voltage. It's the pressure behind it. And then the resistance is going to be the size of the pipe. Bigger pipes, you can get more flow through it. Thinner pipes, not as much flow. And then, of course, the current or the electricity is actually the water itself. And it's a good way to understand electronics because you can think of it as a water tower and how things are flowing. The other thing we do in electrical is we always use the SI units. So you're probably very familiar with gigabyte, like in your computer, gigabytes for memory and for your drives, or even terabyte drives. But we also use the milli a lot. You'll hear milliamps. We deal with a lot of milliamps, especially in the robot. And we have terms like micro that we use. And that is for like microfarads if you deal with capacitors, or microhenries if you deal with inductors. So we do use the SI units, and we use them a lot in electronics. When we go back to our chart here, just to kind of give you an idea of how this works, if you want to light a 2-volt LED that can take 20 milliamps, but you're going to use a 12-volt source, then you have to figure out what resistor you have to add to the circuit. Otherwise, you'll just blow the LED. So we can just walk through it real fast. We're looking for a resistor. Well, we know that's voltage divided by current. We know that there the voltage is going to be 12 volts minus the 2 volts that the LED takes, because we want the voltage over the resistor. And then we're going to divide that by 0.02 or 20 milliamps. So we're going to get a 500 ohm resistor. So that's easy enough to calculate. Power on this circuit, we're going to take the voltage times the current at the resistor. So the power is going to equal 10 volts times the 20 milliamps, 0.2 watts, or 200 milliwatts. So we would use a quarter-watt resistor here. This gives you an idea of how these formulas all relate. Looking at wires, one thing I want to show you on this chart, which is counterintuitive. We use the American wiring gauge standard in the US, and unfortunately it's set up to me backwards. The bigger the wire gets, the lower the number gets. So eventually they run out of numbers and they end up at 0. And then when they want to go to the next wire bigger than this, they have 2 zeros. And we call this an OT, and then we call the 2 zeros double OT. We don't use these in robotics, but it's just there for your knowledge. But just keep in mind, as you get to a smaller number, it's going to a bigger wire. So let's take a look at a wiring chart here. I want you to notice that the wiring chart here, it's kind of hard to read, but it is set up for a 12-volt system, which is what our robot uses. So down on the verticals is all the amps we want to push. And then here at the top is the distance in inches. And this happens to be round trip. So here at 24, they mean that going from your power source to your device back to the power source is 24 inches, or the device is 12 inches away from your power source. So when you look at this, you see a nice little curve here of what happens. Now, wires act as resistors. So again, back to our water tower analogy, if I want to push a certain amount of water through it, a certain distance, I'm going to need a certain size pipe to make sure that happens. So in this case, they're just showing you this nice little curve that's going on. Notice also down here, if they want to do a 24-volt system, then you have to divide the current or amperage in half. So go back to our power law. Our power was voltage times current. So if I double the voltage, I have to half the current because the resistance in the wire is not changing. Just another reference here for this formulas. So let's go look at a robotics rule. So here, this is rule 53 right out of the robotics game manual last year. And we looked at our 31 to 40 amp circuits, which would be our 40 amp breakers on the PDP, require 12 gauge wire. That's the minimum size. You can go bigger, you just can't go smaller. And then 21 to 30 amps would be 14 gauge. Taking that rule and jumping back to our chart, we're going to see something interesting. We're going to see that the 31 to 40 amp, 12 gauge. That's where we see 12 gauge. Oh, look, between 20 and 30 amp, we get 14 gauge. So what FIRST is thinking here is that your motors are going to be no more than 24 inches away from your power distribution panel. And that's probably pretty realistic for a motor that's in the base of your robot. Now, if you have motors that go up on manipulators, such as arms, or at the end of a manipulator, like if you had a claw or something like that, you might have to think about using a bigger gauge wire. Just keep that in mind as you do it. If you're running a motor that's a longer distance to the PDP than 2 feet, you might have to change the wire gauge if you're not getting the performance out of your motor. Speaking of the PDP, a couple little notes besides what Cassie has mentioned about this. These ports here for VRM, PCM, and RoboRio, these are VBAT. What that means is voltage from the battery. This is not 12 volts. Don't ever assume this is 12 volts. If your battery's only putting out 11 volts, there's 11 volts here. That's all it is. None of the PDP is regulated voltage. So this is going out to your first VRM, your first PCM, and your RoboRio. Other thing, this contains firmware. The latest happens to be version 1.4, which was the first update that they put out back in 2016. It doesn't seem to have changed since then. These fuses here are very important, and that is you need to have spares. Sometimes you blow these and you don't know that. The other thing is these are ATM style fuses. They are not ATC. You can buy these fuses at your automotive center. I think they all carry them. That's where I got our spares. But you want ATM. And just think of the other Chicago team, cash money. You want the cash money. So you want an ATM is what you want, not the ATC. The ATCs look really close and similar, but they don't fit. And make sure they're all pushed in, because if you can grab this and pull it out with your fingers, it's not in. You got to use a pair of Unimos pliers, or you got to use a fuse puller to make that happen. Looking at the VRM, Cassie went over this. earlier, and I'm just going to point out that these LEDs here are only on the 500 milliamp rail. That's all what these lights suggest. And so if your 2 amp rail is not working, you won't know that if you just look at these lights. So we look at this in a little bit of detail in the specs. You'll also see that this voltage regulator will work all the way down to 5 volts. And this is weird because you look at it and you go, well, wait a minute, what do you mean it works down to 5 volts? It puts out a 12 volt constant voltage on the 12 volt side. How does that work? Well, go a little bit deeper into it. You'll see they have these units called the SEPICs. These are really voltage regulators, but more important, they are buck boost regulators. What I do in electronics is I will buck the voltage down or I'll boost the voltage up. And there's a minimum voltage that has to come in order for me to successfully do that. In this case, they say it's 5 volts. I really think that it's a buck that's probably a 4.5 or 4 volt buck, but they say 5 volts the minimum to get it to work. So here, and you also see the term DC to DC converters. You guys have probably seen those before. That's a similar, simpler term that's used for these. So here they take it and they will buck and boost it back to 5 volts here. And then they put it out 2 different current limiting devices called PTCs. And these PTCs are really just breakers. If you pull more than 500 milliamps here, what they will do is simply open up the circuit and then give it a certain amount of time, and they'll close the circuit again and let you pull again, and then open it up again. The light turns out, you don't know whether it's the SEPIC or the buck boost that isn't working, or whether you just pulled too much current. You'd have to wait and see if you pulled everything off of here, whether that light came back on again. And you don't have that on your 2 amp side. 12 amp side, or 12 volt side, sorry, is the same thing. It bucks and then boosts. And then they can supply the 12 volts no matter what the battery is doing, because the battery's at 11, it'll still do a 12 volt voltage on the outside. And again, a similar thing here. They just put the LED on the 1 rail. They didn't put it on the 2 amp side. So there's ways to figure this out. You could just add another LED on the 2 amp side, right? So if we were looking at the 5 volt rail, all you got to do is do the same formula. Resistance is voltage over current. We're going to take out the 2 volts for our particular LED. That'll give us 3. We're going to put that over 20 milliamps, and we're going to 150 ohm resistor. We already know doing the 12 volt side, we had 500 from the earlier example. So this is a way for you to do that. Add 2 more LEDs to your VRM and be able to see what's really going on. If they're both out, generally, then your buck boost regulator has fried on you. If only one of these is out, you're pulling too much current. Alternatively, if you wanted to, you could actually connect these to your analog inputs if you want to monitor them with software or the smart dashboard, or if your programmers wanted to log this information. 5 volt rails can directly connect in. 12 volt side, you got to do a voltage divider. A 1 kilo ohm over a 680 ohm resistor is perfect for this. You'll see it would be about 7.14 volts over the 1K and about 4.86. It goes over to 680. And that is perfect for doing the electron. Looking at the PCM real fast, it does contain firmware in it, so you have to make sure that your firmware is up to date. There are status LEDs on this, which is really cool. And then the bigger thing on this is the compressor, whether you want to turn it on or off. You don't need to define it in the software if you don't want to. This will automatically turn on the compressor if this switch is shorted. It will turn on the compressor. But there are times during the match you don't want that to happen. So you may not want to happen during autonomous, and you may not want it to happen at the end game. So like this year or last year with climbing, if you don't need the air at the end of the match, why do you let the compressor run and then pull current from your battery and slow down your climbing motors? It's something for you to keep in mind. You can get the match time out of the driver station software. So you can actually see what time is left in the match in software, which is really cool. Do a little dive on the spec sheet on this. we're going to get to those buck boosts again. Here on the input voltage, you see the solenoids, 12 volt solenoids operate between 11 volts and 16. However, my 24 volt solenoids will work between 5.5 and 16. I'm telling you, this is the best answer. If you can, switch over to 24 volt solenoids. Look at what they say down at the spec sheet. Note 1, PCM functions below 11 volts. However, 12 volt solenoids may not engage. So if you've ever had your robot out on the field, your drivers have been driving around, and all of a sudden pneumatics aren't working, and then you get back to the pit and they work just fine, it's probably because you're using 12 volt solenoids, but your battery wasn't at 12, wasn't above 11 volts when you tried to fire the pneumatics. However, if you just do 24 volt solenoids, you can see here PCM boost, there's that boost term again, solenoid voltage 24 volt, allowing the solenoids to be fired in low voltage conditions. If you do this, you're safe all the time because your RRIO is going to power off at 6.3 volts. So if your battery got down to 5.5 or below 5.5, you're kind of dead for the match anyway. The other thing here, when they use the compressor output, they tell you to use 18 gauge as the minimum gauge to use for the compressor. However, those Webuller connections will take 16 gauge. This is about the bigger pipe again. So we want to get as much current as we can to the compressor, so give it a bigger pipe. So go with a 16 gauge wire because that's the largest thing that'll fit in. Moving on to the radio. This is that old D-Link radio that we used to use. It was the DAP 1520 radio that we had. So there was a symbol on this, and this is the symbol for a barrel jack. What this means here is that the positive is on the inside of the barrel, the negative goes to the outside of the barrel. You'll also notice on a lot of these barrel jacks, there'll be one wire that's black and one with black and a white stripe. Sometimes I've seen them where they're both black, but one of them has a ridge. And so the ridge will indicate that that's the one with the white stripe. This would be the positive lead, and the solid black would be the negative lead, typically. The best thing you can do for yourselves is take a piece of shrink tube, red shrink tube, or red electrical tape, and mark the one after you verify it, which one is the positive. Because these radios are $135 a piece. And if you've misconnected this, then you will fry the radio because, as this note says, there is no reverse protection, voltage protection on this device, and it does smoke. Because I know because we've done that before. So make sure you verify this. Don't just assume that that's true. Make sure it, take an ohm meter, check the lead, make sure it's true, and then mark it when you're done. Go through and pop in and look at some analog real quick. We'll just peruse this. You had the 4 ports on the RRIO, but you actually got 4 more on the MXP breakout board, which is nice to have. And then on the MXP, you also have 2 output ports that you can use. Analog inputs are 0 to 5 volts on the RRIO. The inputs are 12-bit though, so this is really good for measuring potentiometers, like if you're measuring the angle of an arm or a lift or something. It's really nice to have the 12 bits instead of the 10. The analog outputs are 0 to 5 volt as well. That's great, but they're only 3 milliamps. So keep in mind, you're not going to power LEDs with this. This is really used as a voltage device to get back to the analog inputs, which are just purely looking at the voltage. Do not attempt to read the 12 volt signals with the analog inputs. Do the same thing we did on the BRM. 1K resistor over a 680 ohm resistor, and then that'll max out at about 4.86 volts, which is great because batteries really go to 13 and a half volts when fully charged. So this works out really perfect for you. The other thing is always use high quality potentiometers whenever you're doing this. A lot of people like to go and find a cheap potentiometer. You don't want that because they're noisy. So as you turn them, instead of this value going up or down smoothly, it oscillates and it jerks all over the place. You do not want that in your software. So Cherry Electronics, we've used those before. Cherry Electronics makes some fantastic potentiometers. Don't buy Radio Shack. Now I know Radio Shack's out of business, but they're actually coming back as an online store. You don't want Radio Shack parts. Go buy the nice potentiometers. Looking at digital I/O, and this is where the meat of this talk is. So let's go dig into this. When you're looking at sensors for your robot, there are two types of sensors in the electrical world. There are NPN sensors and there are PNP sensors. They are not the same, and do not confuse them. The other terms we use for these is syncing and sourcing. And these are kind of better terms to think about because they're more understandable. If you look at this one on the left side, and we've got a relay circuit setting here. These guys are taking 24 volts in. They're tying the positive to one side of the relay. The other positive goes into this prox sensor. So the prox sensor gets powered by 24 volts, and the prox sensor is connected to ground. That's great, because it's got electrical components in here. Now, when a piece of metal comes in front of this, what this device does is it connects the signal lead to the ground lead. That's why it's syncing, because it's trying to find ground all the time. So this is dead when there's nothing out here, but when that piece of metal gets here, this, all it does is open up and takes this lead and ties it to the ground lead, and we sync it. The other term you'll hear periodically is open collector. If somebody says it's an open collector device, they mean it's an NPN device. On the contrary, PNP is always sourcing. So here we do the exact same thing. We take the 24 volts, we put it into our prox sensor, but here the prox sensor is connected to the positive lead on this relay, and the ground of the relay is already connected to ground. So what we're messing is this positive voltage here. When the piece of metal gets in front of this prox sensor, what it will do is tie the positive lead to the signal lead and send voltage out here, and this will now power this relay. It is two different ways of doing things. And what you need to understand is that in first electronics, it is NPN. Everything is NPN. So if you've bought a sensor before and it didn't work and you didn't understand why, and it's like, well, I don't get this. I don't understand why the sensor doesn't work. It should. It says it does. Well, it's probably a PNP sensor. That's why it doesn't work, because it's trying to source voltage, and we have things in the robot that automatically give voltage to the digital input pin, which is what we're going to talk about real quickly. So you want NPN. So in looking at digital I/O, how would you hook up a switch? You could do it three ways. You could hook the positive lead up to the switch and then put that to ground. That's one way to do it. You could take the signal lead and go through the switch and then go back to ground, or you could take the signal lead, go up through the switch, and go back to positive. So which way is it? Or is it none of the above? Do we not hook switches up this way? Well, the answer is going to be B. A is obvious because you can't take the positive and go to ground. You're just shorting out the power. That's not going to do any good. Most people think it is C. Because why wouldn't I take positive and send it to my signal? Aren't I trying to get a logical one out of this? Now, a lot of people argue this point, and they say that makes no sense to send it to ground. Why would we ever do that? I need you to prove that to me. Sure enough. So let's go look at the Talon SRX user guide. And notice how they've connected this switch. They've taken the forward limit switch, they've connected it here, and it goes to ground. It does not go to the 5 volts. And in fact, the reverse limit switch would do the same thing. They mentioned up here about these external pull up is not needed. So let's go figure out what that means. When you're doing digital I/O on the REO, this is how it's set up internally. There is actually a resistor in here between power and the signal lead that you don't see. It's there. So think about what's going on here. If I have a switch and it's open right now, and I have voltage here, voltage goes across the resistor, And most people think then it's 0. But the problem is this is not grounded. There is no circuit here. I have voltage but no ground, which means the voltage that's here is also on the other side of the resistor. And in fact, you can daisy chain resistors, and the voltage that you send in at the beginning of the circuit will be at the end of that resistor chain as long as you haven't grounded it yet. We can't do the voltage division over the resistors until it's a circuit, until it's grounded. The signal lead here is not a circuit. It's really a voltmeter. So the voltage comes in and it goes in and does this. And you go, okay, that's great. When the switch closes, now I have a circuit, the voltage drops over the resistor, and now I have ground reference up here in the signal. And you can say, okay, but that would mean I should see a 1 when the switch is not closed, but I see a 0. And you can prove that with the software all day long. So why is it like that? Well, let's go look into another manual here. Let's go look in the Talon manual. Note down here, the sensor being closed returns true in all cases. When it's closed, when it's shorted to ground, it returns true in all cases. And the sensor being open returns false in all cases, okay, regardless of normally open, normally closed. What we do in the REO and in the Talons is they invert it. So whatever the signal is, they say, if it's a 1, give them a 0. If it's a 0, give them a 1. That's all they're doing. They're just inverting it for you so that logically it makes sense. And you say, okay, well, let's go into the data sheet here on the REO itself. Digital I/O pins 9 down to 0 here. They have a 40K ohm resistor tied to 3.3 volts. That may confuse you thinking that it should be 5 because we do digital I/O at 5 volts. It's called 5 volt compatible. And that's because the threshold for a high value is 2.7 volts, which works for 3.3 and 5. And the same thing on the 0 side, it's 2.3 volts or lower is a 0. And that's compatible with both 3.3 and 5 volt. So they just tie it up with a 40K ohm resistor, waiting on you to ground this thing, is what they do. We also have this concept of pull down resistors. Pull up resistors are on inputs. Pull down resistors are on outputs. So here, if I'm trying to send out a signal, like here on the clock or the MOSI, the MISO, I'm trying to go out on this. So I don't want it high all the time because I'm going to send a high signal and then I want it to go ground. So here what I do is I tie this pull down resistor to ground. This will drain all the voltage out of the line until my REO sends out a 5 volt signal. Then that 5 volts will get dropped over the 40K, but I have 5 volts on my line. Therefore, I can signal. When my REO stops putting out 5 volts, this 40K pull down resistor pulls the rest of that voltage out of the line and makes sure that my device on the other end isn't seeing anything. Okay, so if we did all that, so what's this plus sign? What's our positive 5 volts doing on digital I/O if I don't need it? Well, I need signal and ground. What am I doing with it, right? Well, that's pretty easy. I got devices I got to power. A lot of times the encoders are all 5 volts. But then what happens if I got things like line sensors or I'm using an industrial controller that runs at 24? How do I do all that stuff? Well, that's okay too, because I can just come off the PDP if I want to go 12 volts, or I go through another buck boost module to get to 24 volts. That's easy enough, and I tie it to the PDP. The real question here on this device is I have 2 output wires, and this is typical from a lot of industrial controllers that you might use on your robot. They have 2. They'll have a black wire and a white wire, and you'll say, okay, why do I have 2 wires for signals? Well, the issue is this. They'll be labeled NO and NC. And NO stands for normally open, like on a switch, or normally closed on a switch. So these 2 leads will have opposite values. So the question is, which one do you want to use? You could use either one, it doesn't matter. Notice over here too, that I've got this brown wire for my positive and my blue wire for my negative. A lot of industrial sensors are wired this way. And that's why in our game manual, you'll see this rule. So red, yellow, white, brown, or black with stripe with our barrel connector on the positive side, and black or blue on the negative side. So we have this rules to cover this, so in case you need to do this stuff. Now, of course, down here, C tells us that if it's already wired, it's legal. No matter what colors they used, it's legal. But this gives us the ability to do things with different colored wires other than just the red and the black. So going back to our normally open, normally closed, the question I have for you is, can you use both at the same time? Now, obviously not on the same signal pin, but can you plug both of these in? And if you can, how would you do that, and why would you do that? Why would you ever do that? Well, let me give you something to think about. Let's say we wire them both, two different signal pins, and we label one switch normally closed and one switch normally open. This little symbol here, this little caret, in programming, that is called an exclusive OR. So exclusive OR says that one of these can be true, the other one has to be false in order for exclusive OR to be true. If both of them are false or both of them are true, then exclusive OR is false. And I know that sounds confusing, but you can go look it up and it'll make sense to you. So here, this is just a little piece of code that kind of explains this. So if my switch normally closed, exclusive OR with my switch normally open is false, that means something's wrong with my device, because that can't be for a device that's working. So I got an error in my switch. So I set my switch OK to false. Otherwise, I'd set it to true. And then somewhere in my code, I come in here and I say, is the switch okay? Well, if the switch is okay, yada, 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 I go through my normal code. Otherwise, I do the yakety yak, yak, yak. The reason you want to do this is to stay in the game. Keep in mind, you've paid $5,000 to be at an event, and you get about 10 matches. That's $500 a match. So you want to stay playing. So stay playing. So do things to help you figure out whether a sensor went bad. And then have it already set up in your code to deal with it. Notify the drive team. Have an override. Do something so that you don't sit there and say, oh, I'm down. I can't play offense. I'm going to go play defense now. Well, that's not what you want to do. You want to play offense. So make it happen. Make sure you have code in there to do that. And don't just cut off one of the signal leads and say, I'm not going to use it. The other reason to just do both signal leads is simple. If I have both signal leads in there and one of them doesn't work because the wire got cut, tell the programmers to use the other port and invert the signal, and they'll be fine. Okay, let's go through encoders real quick. Encoders, these are two-channel devices, and they're direction oriented. So here, if it sees the B channel go high, followed by the A channel going high, I know I'm going clockwise. And just the opposite. If I see A go high, followed by B going high, I know I'm counterclockwise. That's all the encoder works, and it's just looking at the light and dark spots on the wheel here. That's whether it sees light. How you wire them up? Simple. 2 signal pins. You just hook up 2 signal pins. You got the positive and negative off of one. Hook it up. Everything's okay. If the encoder's going the wrong direction in the software, you can set the inverse. All the encoder code for FRC, you can always set inverse, and it'll go the right direction. The other thing you could do is rewire that, but that's not suggested. If you rewire this, then you could have you could have green, yellow, followed by yellow, green. You don't want to do that on the R relay. You want to look down the side and see all the colors alternating. Counters are the same kind of thing, only there's just one signal lead, so they can't tell direction. They only count up. Okay, running through some motor controllers. Us old timers know what these things are. Then there's some more newer motor controllers that we have, and then finally some of the newer ones. And Cassie went into some detail on some of these, and I'm going to follow up a little bit more detail. Talon SRX here has a breakout board. Notice 5 volts here, forward limit switch, reverse limit switch. It also has 3.3 volts. That's really for its analog input, so you can run this to potentiometer. And here's your quadrilateral input. 3.3 volts is 33 milliamps. Again, like the RRIO, it doesn't have a lot of current because it's really a voltage. It's trying to use it with the analog. You can use 5 volt analog if you want, but you got to use their breakout board, and then they will convert the 5 volt analog back to the 3.3 to put it on the input, which is really cool. It is firmware updatable, and the 5 volt only has 50 milliamps. So if you have a limit switch or something that has an LED on it, make sure you check how much current it pulls, because you don't want to pull too much current and then fry this port out. Limit switches work even in PWM mode if you use PWM mode, and that's because the limit switches are directly tied to the controller, and they work. You don't need feedback back to the RRIO. Spark Maxes, they have a input for their own Neo, and it's got the same thing: ground. It's got A and B channel. It's got a temperature sensor, which is really cool, and the 5 volts. Thing on this slide to look at is you could run this in brush mode. So technically, you could actually run your entire robot with Spark Maxes, whether you have brushed or brushless Neo motors, if you just wanted to do that and make your life easier. Other important thing about the Spark Max here, this port here is absolutely identical to the Talon SRX. In fact, you can use the same cable on it, which is nice if you run both. Here, when in brushless mode, these data port pens cannot be used with an external encoder. Okay, in brushless mode, you can't use an external encoder. You can only use the Neo encoder. When in brush mode, the external encoder can be connected through either of the data port, or it could be connected where the Neo port is. So it just kind of runs through it. Also notice this: the Spark Max encoder signals are not pulled high, pull-up resistors. But they don't do that internally on the Spark Max. This is to ensure the maximum compatibility with different types of encoders. So this is more open, and if you ever run an external encoder with a Spark Max and it doesn't seem to work, probably you need some resistors, pull up or pull down resistors to make it happen. Sim Venom. This is a new motor, replacement of the Sim. They also have a little breakout board you could buy. They have an analog input and then forward and reverse limit switches. Interesting thing about this is the limit switches are disabled on power up, so you have to turn them on in code. Otherwise, they ignore it. It is a brush motor, just like the Sim, and the shaft encoder I think is 1024. Looking at the equations that they give, it looks like it's a 1024 count instead of 2048. Talon FX. This is interesting here. Notice reverse, ground, forward, ground. Again, it's an NPN device. They're trying to find ground on here. It is brushless, like the Neos. Internal shaft encoder is 2048. It also whistles when you stall a motor, which is kind of cool. I've never heard one yet. Can't wait to stall a motor and find out how it whistles. It does have a pneumatic exhaust port, which is really cool, because with a pneumatic exhaust, you can actually blow air into the motor to help cool it off between matches. Firmware updatable, and then the library is compatible with the SRX, but you can't use master follower. So if you do master follower, like on a drivetrain, you can use a Talon SRX and like a Victor together, or two Talons together, and that's great. But just because the Talon SRX and the Talon FX use the same library, you cannot use them as a master follower because the motors will drive differently and one will push the other in the gearbox. Okay, one other thing about the Talon FX. Notice this note down here. The Talon FX has built-in reverse polarity protection. This ensures that the Talon FX isn't damaged in the event of power polarity is reversed. However, it won't work. This is the only, and I mean that, the only motor controller legal in first that has reverse voltage protection on the input, which is really, really cool. So make sure you have to watch your wiring on everything else but the Talon. If you got it wrong, your motor will not fry. Okay, real quick, powering up the robot. You want to remove all your breakers except the 10, 20 amp minis that are in the PDP. You want to leave the radio disconnected. Power on, verify the green lights. Make sure that the RRIO powers, the stat lights on the PDP is okay, status lights on the PCM, and the VRMs are okay. Then you want to take a voltmeter and check the polarity on that radio barrel head connector. Make sure it's plugged in right. If it is, go ahead and plug it in, see the radio come up. One at a time, insert your snap action breakers and make sure that each of your motor controllers or your combined motor controller motors fire up just fine. And then functionally test everything. Make sure the motors are going the right direction. Make sure your sensors are sensing. And remember, if anything has to be reversed, do it in code, not in the wires themselves, because that gets confusing. And then, of course, being electronics, we want to defend our electronics from mechanical teams drill, because we already know that they're going to be drilling on the robot, dumping aluminum shavings into our electronics. And lastly, label your connections, create an electrical schematic, extras of everything in the electrical box for the regional, just everything, take extras. Locate all your electrical wires away from moving parts and keep your wires away from the motors because of the EMF. The coils inside wires generate an electromagnetic force, which will interfere with all your signal wires. So make sure you try to run them away from them. And with that, we are done.
All right, Ron, thank you so much for presenting. That was fantastic and so informative. We have a lot of good feedback in the chat, so I'm just going to read off a couple questions. So Mona says, thank you for the presentation. She thinks it was great. And she's wondering if there's any wise words to pass down to students who are looking to study electrical engineering in undergrad. So do you have any advice that you'd give someone to, or who's considering working as an electrical engineer?
Yeah, I would go through and look at what exactly do you want to do. Electrical engineering has changed since I was in college. So there's specific fields now in electrical engineering. You can do power systems, you can do computer engineering, electrical engineering. There's just all kinds of stuff out there. I know where I work at Nokia, we have electrical engineers that specify, I actually didn't think of the term. They specialize in radios. So electronics is very varied, and one type of electrical engineer doesn't mean they can do everything in electrical engineering. So you get to find out what you want to do, and then go see if you can find somebody that does that work. Go do some research, see what it pays. I tell that to all students: find out what you think you want to do actually pays, so that you can actually make a living off of it. But that's my suggestion. Go see what you really want to do, and then go hunt down people that do that.
Perfect. Thank you so much. Asher is kind of following up with that question, and he's wondering sorry, let me find the question a moment. Here you go. So if you would recommend a major in computer engineering for someone who's interested in both fields, so someone who might be interested in electronics and also computer science. So computer engineering is the focus of this question.
And that's another thing, and I hate to say it, I've been out of school for a while. So when I went to school, you did electrical engineering or you did computer science. They didn't tie the two fields together. And now they're tied together, and they're down. There's many different degrees that you can go get. And unfortunately, I can't answer your question because I don't know all the specifics. I know our students tend to do that too. They go in for a combined electrical. I know there's a robotics focus that you can go for now with electrical and programming. And then there's industrial controls that does electrical and programming. So again, I would just go hunt down exactly, figure out in your heart of hearts what you really want to do, what excites you, and then go find people that do that and go ask them, so what do I do? What do I do? And go find schools that specialize in that.
That's great advice. Thank you, Ron. Those are the questions that have popped up in the chat. I'm going to leave the chat open. So if anyone has questions, feel free to drop it in the chat, the live chat here, and I can always pass them along to Ron. Ron, thank you so much for your work, and thank you for all of your knowledge and sharing it with us today. Is there one last piece of advice that you'd like to send out to anyone who's watching today?
Sure. I mean, one thing I want all the students to know, and even the mentors, first is a cooperation. And that means we compete with each other, but we also cooperate with each other. And I have found through my years of FIRST that I get more out of this when I work with other teams. And um, as students on your teams, as you're doing things, reach out to other teams. Um, we have we have made on our team a lot of friends with other teams, and then during the build season, we actually get on conference calls with them, and we talk. We talk strategy. We talk about things that are going wrong with the robot, and how would you guys suggest we do this, or uh, you know just the gamut. So don't think like during the build season, well, I can't talk to anybody. Nobody's going to talk to me. That's not true. Um, we're here for the students. The mentors are, and uh, mentors will help students on any team. I know our team does that. We reach out to students that have problems on a team and they don't have a mentor that is a programmer or isn't an electrical engineer, and they're struggling with a new sensor. They're struggling trying to get some code work, and they'll contact our team and we'll work with them. Bring them over to our shop, or we'll go over to their shop. Whatever, it doesn't matter. So the whole point is to get you guys excited about a career. I know we mostly focus on STEM, but it's about getting you excited about a career. And the mentors are here to help you. And don't think that you can't go to another team and ask for advice or even just see what they're doing. I was just, real quick, I was just talking to Jack because he's doing a presentation right now doing robot design. And I really wanted to be in Jack's presentation because I want to learn from him. I want to know what Argos does. I want to know how we can benefit from that.
Well, we have one last question from Nadim, and this will close out our time together. So Nadim is asking, when it comes to motors, how do you decide which motor is best for the task at hand? And then how do you figure out how much a motor can handle before stalling? So how do you make your choices in the motors that are going to perform? And then how do you actually do the math to figure out if your motor can handle that task?
Okay, so and I'll give a caveat here. I make the mechanical team do all that work because they know what the load, the torque that's going to be required. All the motors that we use in FIRST have a specification chart, and you can go get them. So you can go look and see what the torque is at different RPMs of the motor. And then you have to go back and look and say, okay, so I have this mechanical thing. How much torque is it going to need at this gear ratio to make this happen? And then that'll help you decide on what motor you've got to use. Keep in mind, your best efficiency of a motor is at half its max speed. So if you're looking at a SEM, and a SEM runs at basically 5,200 RPM full out, you want to design your mechanism so that if you're running it as fast as you want to, you're at 2,600 RPM. That'll give you the most efficiency and it'll give you the most torque. So go to your data sheets and go look at that. There's also Chief Delphi. Go throw something out on Chief Delphi. You will have a bunch of mechanical engineers that will quickly answer your question on that.
Great. Thank you so much, Ron. Thank you so much for all of this wonderful information. And just a reminder to anyone who's watching, this will be available for your access as well after after we're finished. So thank you, Ron. We're going to take a short break before we move on to applications of pneumatics with Natalie. Ron, thank you again. And to anyone who's watching, we'll be back shortly. All right, everyone. Welcome back to Stream 3. We are about to get our third session for the day underway. This is Applications in Pneumatics for FRC, and it's Natalie from Team 4645, the Chicago Style Bot Dogs, who will be presenting to you. Natalie is a senior at Lane Tech High School, and she is the sub-team lead for our pneumatics sub-team. So in just a moment, she's going to join us with FRC Pneumatics. Enjoy.
Hi everyone, so I'll be presenting today on FRC Pneumatics, what pneumatics is, why we use pneumatics, and how to use pneumatics. So I've been doing pneumatics and learning about it since my freshman year, and I am now a senior in high school. And over my years, I feel like I haven't seen a lot of teams use pneumatics a lot. And I feel like it's something that teams should be using because it's very helpful to use in a lot of ways. So move on here. So what is pneumatics? Pneumatics is the manipulation of air. I like to call it air magic. So we basically create these loops that store air at extremely high pressures in order to use it as mechanisms, as just fuel, as power. And why? We got a few text here. It's less moving parts, which it means less points of failure compared to a lot of moving gears and parts. There's only really one moving part in pneumatics at all times. Extremely powerful. Last year, our climbing system, our robot 4645, could exert 158 pounds of force with only one piston, and we had two pistons mounted on both sides of our robot. It's also extremely reliable, where there's basically barely ever been a match where something went wrong in pneumatics. There's very little things that can go wrong, and it's extremely versatile. Basically, anything that can be done with motors can also be done with pneumatics, and a little bit more. So here's just a lot of text, but it's just some previous uses of what people have used it for. For power up, we use gear shifting, and a lot of people use it to actually grab power cubes, and I've seen it in world competitions. They even use pneumatics to grab it there. It's very adjustable, and they're very strong, so it's very hard to get the cube away from you. It's also very fast. And then for D-Space, again, we used gear shifting every single year. Also climbing, we use pistons for climbing in D-Space as well. We could do a level 2 climb very consistently and quickly every single match, and there is basically never a match where we didn't climb because it was just so powerful and very efficient. It's very easy for the drivers to use because there's a very high margin error that you can fall into. There you go, and more D-Space. Again, hatch placement, that's how we would push the hatch off of our robot and place it, is very easy. And also for ball grabbing, same as the milk crates. And for infinite recharge, of course, more gear shifting. And the reason we use gear shifting with pneumatics is so we can go into high and low gear. And one of the gears, they allow our robot to be extremely quick so we can sprint across the field in mere seconds and get to a place where we need to be. And then we can just quickly shift to a different gear and become this unmovable rock. And it's very, very valuable for defense. And almost nearly every single year, we're really good. Our robot has always been an amazing contender for defense because we always have this gear shifting mechanism. We also used it for climbing last year, and this is a part of a robot that everyone was always so drawn to. We used two huge pistons in order to lift our entire robot off of the ground and get very easy points there on the leveling and hanging. And there has never been a time where we didn't climb. Like we've had times where we had to climb with even only one piston, and we are able to do that. Two pistons is just overkill, and that's in like this scenario. But we still had it, and there was never a single time that we didn't climb. So this is how. So this is a lot of stuff, but they all come in the the first kit of parts for rookie teams. And everything here is included except for the pistons. Pistons are not included the kit of parts, but everything else is. So it's very, very easy for a rookie team to get started using pneumatics. So we got PCM, compressor, pressure relief valve, pressure switch, pressure gauges, pressure regulator, and we're just going to go all over every single one of these parts in the presentation. So first we got the pneumatic control module, which is the brain of everything, basically. It powers the compressor, it allows solenoids to be controlled remotely, and there's a pressure switch that's also connected to it for a fail-safe just in case the pressure gets too high. And as you can see in the picture, that's basically how everything's connected. There's also CAN wires that we attach, that we can daisy chain, and then that's how we get information out, in and out. I'll show more of that later. And we got another thing, the compressor. So from its name, obviously it compresses air, increases PSI, which stands for pressure per square inch, which is basically how we can gauge how much fuel we have. And this is the component that kind of creates everything that we work with, pressurized air. We need pressurized air to do everything in pneumatics, and this is how we get that pressurized air. And just like for safety stuff, this compressor, it is very dangerous. After period like a few minutes of usage, it gets extremely hot. You do not want to touch this. You do not want to brush it. You do not want to be very close to it when it is in use for a long time, or if it has been in use for a long time. It's also shakes a lot. If you don't mount it down with anti-vibration pads or mount it down at all, it will shake right off of the table or right off your robot if you don't mount it. So you have to do that. And the compressor that is given to us by first, it will take a lot of time to fill up the system, and it's all kind of dependent on the compressor CFM, which is cubic feet per minute, which is basically how we measure airflow. The maximum CFM that first allows us to use is 1.1. I believe the one that they provide is about 0.85 CFM. So you can get better one, but it's not very needed because depending on what you use, most of the time we're not going to be using it for extremely big projects and such. So this compressor is just all right. We've got the first interface that I mentioned earlier, the pressure switch. So this is the ones provided us by first. It's calibrated to max storage pressure. But what this is basically it will shut off the compressor when the pressure threshold is hit. The pressure threshold for the pressure switch is 120 psi, which is the max storage pressure. We'll talk more about that later, but the storage pressure, this has to be mounted on the storage side, and once it hits 120, it will shut off the compressor, so we can't go above it. And this is electrically controlled, not mechanical, and you'll see why I mentioned I have to specify that. So we have the second failsafe, which is the pressure relief valve. This is calibrated to 125 psi, just 5 psi above the pressure switch, because if in any case the pressure switch fails, we have something else extra to make sure our entire system doesn't just explode. And the pressure relief valve is entirely mechanical. It's just a spring in there, and you can adjust it by turning the knob, as you can see on the picture on the right. And the one on the left is hard set to a certain PSI, so you cannot control that. So those are two fail safes that we need on our robot in order for our robot to be first legal and for it to not explode if something bad happens. And now we got the pressure regulator, which separates high pressure components from low pressure components. Basically separating our system into two parts, which is high pressure and low pressure, or people call it storage and working pressure. Storage pressure, as I mentioned earlier, can only be the highest it can be is 120 psi, whereas the working pressure, the highest it can be is only 60 psi, because the working pressure, what it means is like where all of our moving components are going to be, like pistons and such. We don't want our pistons to be shooting out at 100 with 120 pressure per square inch. That's too much power, and also a lot of the pistons are not calibrated for that, or not manufactured for that pressure, aka it will probably explode. And a really important thing that I cannot stress enough is that the pressure regulator only regulates stuff in one direction, meaning only dependent on the arrow. There's an arrow on the pressure regulator. It will show which outputs are going to be calibrated to 60 psi versus 120. And it's not, the pressure regulator doesn't do anything to the other side, basically the storage pressure. It only affects the working pressure. And if you accidentally turn this the opposite way, you're gonna be very confused, because your working pressure is going to be 0 psi and your storage pressure is going to be 60 psi. And embarrassingly enough, our team has had a few problems with that. So I just want to emphasize it, that you have to make sure the arrow is pointing in the right way. And the pressure regulator can be adjusted via knob. So you just lift it up, you hear a little pop, and you can turn left or right to adjust the pressure that you want to calibrate to. Of course, we want to calibrate it to 60, but for gear shifting, sometimes we only use 15 because we don't need that much, and 60 is a little overkill. So you can chain them to have multiple different PSIs in your working pressure, as long as it's below 60. And now we have the solenoid, which is another very, very important part of our system. It's basically how we remotely control the flow, how we can tell the pistons to either retract or extend. This is how we tell them. It is electromagnetically controlled, which I think is really cool. And well, there's a lot going in there mechanically, but basically what you can see is that there's kind of like a little tab in there that when you activate one side, it'll move the tab over and then open out one of the valves so air can flow to the specified side of the piston that you attach the tubing onto. And if you activate the other side, it'll shift it to the other side. There's many different types of solenoids that we'll go over a few later. But here's our piston. This is how we normally utilize our cool pressurized air. So it's most common. And so the piston can only move kind of up and down linearly, but you can combine it with lots of things to make that energy go in different directions. And so we have our two most common types of pistons, one called single action and one called double action. So the single action pistons, they only have one port. If you see both pictures that I have on this slide right now, they both have two ports, meaning they're double action. Single actions will only have one port. And that's because the way it goes the opposite direction, like when there's no air being put in, is that there's a spring. There's a spring inside of the piston that will yank the the bore either extended or retracted, depending on what kind of piston you have. So say you have the air port is on the bottom, so you can see just like that piston, but imagine the air port is on top, is not existent. If you were to put air into it, it would extend the piston, but then once you stop the air from coming out, there's a spring inside that will yank the piston back into position. So that's how single actions works. And double action is they have two ports, and how there's no spring inside. It's just it moves freely basically, and so it can kind of stay in place, and you can kind of control it more. And that's what we usually use double action cylinders, but sometimes single action might be better for the job. And here's just a really rough sketch of what goes on inside of a double action piston. You can see there's kind of like this airtight seal that's inside that separates the piston into two separate chambers. And if air goes into one side and it fills it up, it will either retract or extend. You can see depending on which side. And so another important part is a vent valve, and it's used to just quickly release all the air in the pressurized system, or it can even be used to restrict the airflow and lessen the CFM, but we don't typically use it for that reason. These are usually just for venting out air. And this is just required by first because if something has gone wrong and we can't use any of the two fail safes because those are only for very high pressures, right? But if your system's only at 60 psi and stuff is going insane, you need to be able to just get all that air out right away. So we need the vent valve on the robot to be very easily accessible, just in case something goes terribly wrong. And we've got the fittings, and it's kind of what we combine with tubing in order to kind of put everything together. So it's just how we connect all of the components that we described before: the pressure relief valve, the pressure switch. This is just what we attach it onto with threading. And there's also push to connect stuff. If you see the stuff that doesn't have threading, that's where we put in tubing. That's how we build our systems together. And then here we have the tubing. It's another way to connect all the pneumatic components together. This is typically when you need to you need to attach pneumatic components that are like all the way across the robot, such as pistons and your vent valves or your gauges, because your gauges need to be very easily seen on the robot. So usually we tube it up so we can get it to somewhere on the robot that we can see very easily. And same with the vent valve, we need to be easily accessible. So use tubing and move it somewhere far away from the main system so we can use it easily. And then of course we have the pistons, which will typically be pretty far away from the rest of our stuff. And that's why we use tubing to get it there. And there's a lot of different kinds of tubing. The one that's provided to us by the kit of parts, the rookie kit of parts, is the black tubing, as you see on the side. But in my team, we like to use color tubing as well because it's very easy to color code stuff. And when you're using more complex systems with a lot of tubing going around, it's extremely helpful to see like which parts of the system are high pressured, which parts are low pressure, which tubings indicate intake or extending or retracting or outtake. So that's why we like to use colored tubing. And of course, there's also coiled tubing. So if you're moving, if your moving parts are also moving, aka the pistons, if the pistons are moving around, it's very important to have these coiled tubing so it can easily move away from the starting point or back, just like a spring. And now we're going to go over to assembling the system or loop, which I have a cool little video demonstration. Just give me a second here. We see here, I have a little system set up here. Let's stop presenting for a quick moment. And just give me a second to adjust here. All right. Get my little chair. All right. So what we have here is a little system that I've set up already. And we can see here is the compressor. We have the PCM here. And then we have all the other stuff that we'll show you. I'm going to move my camera a little bit so I can show you guys here. So this is the PCM. Ooh, I don't know you guys can see it. All right, here we go. So this is the PCM. It's a little clogged up here right now, but you can see here on the PCM, we have these CAN wires, which are used to communicate with the rest of the robot and programming. This is the VIN, which is how we get power to this component. Over here is the pressure switch and compressor out, which is where we attach the pressure switch and compressor. You can see they're right next to each other because they're related in the sense that the pressure switch will shut off the compressor if the pressure gets way too high. You can see here is all the other ports for solenoids. This is where all the solenoids go, and the ports that are labeled with numbers is what programmers will actually this is how they're labeled in the programmer side. So if they want to activate 0, port 0 is whatever the solenoid will be connected to. If I'll show you a solenoid right here. This was connected to piston already, but so solenoid right here, you can see here is there will be two. This is double solenoid because you can tell there are 2 connectors on each side. And on these connectors, there will be usually another connector that has wires coming out and will attach onto the PCM in one of the ports. And if that port is being called by the programmers, it will activate whichever wire is connected there to the solenoid, and it will push it out and activate the pistons from there. Move this back. So this is the compressor. You can see here, I already have some fittings here. In my system right now, I do not have a pressure switch. And the reason for that is there's no way for me to use it. Because you see here, I don't have the compressor connected to the PCM. And that reason is because I cannot turn on the compressor without programming if it's connected to the PCM. So we're just having direct power into the compressor. And how we activate it is I have a circuit breaker right next to me for me to turn it on whenever I need to. So the only thing we have connected here on here right now is the pressure relief valve. And that's really important to have very close to the compressor, or just attached to the compressor just like this, because we just need it on the system. And the reason we don't usually put the pressure switch here is because the pressure switch also needs to be connected. Oh, this is the pressure switch. The pressure switch needs to be connected to the PCM. And sometimes wiring can be difficult, and it might be easier to move the pressure switch closer to the PCM in order to have the wiring not be as bad. You can see here the pressure switch has 2 little prongs here, one for each wire. We just connect it onto the PCM. And from here, we can see we can follow this tubing. And I have a split off right here with a T connector. It's all push to connect fittings. And what push to connect is basically a very easy way to connect these tubes together. And how we get them off, I will put this down right here, show you. Oh, trying to, okay. All right. So this is the push to connect fitting right here. I've attached to this pressure regulator. But this push to connect fitting, you can see there's tubing in there. And all you need to do to remove it is push these 2 sides down, like push this little black part of the fitting down. Need a little force here. And then you can just pop the tube right out. You couldn't see that too well there, but you can see all you have to do is push this little black part down. Like click down, you'll feel a little click, and then you're able to freely move the tube out. And the reason for that is that inside of this push to connect fitting are little kind of teeth that they'll stick on to the tube when they're connected like this. But if you push down this little black part, the teeth go flat, or they get pushed outwards, so they're no longer kind of attached or chewing the tube, so that you can just yoink it out right there. We'll keep this connected for now. Make sure it's a good tight fit, because you'll feel a little click. And if you don't have a good fit and it's not all the way in, you will have leaks here. And leaks are not good, because pressurized air is always going to try and get out in any way it can, because of physics. Basically, high pressure always wants to go down to low pressure. It's just trying to reach an equilibrium. And the higher the pressure, the more so it will want to get down to low pressure. So it's always important to have really good and tight fits on everything, so we don't have any leaks. And talking about leaks, we have something here called Teflon tape. And Teflon tape is something that we put onto threading, such as this fitting right here, to create a really good seal. Because by itself, threading still has its gaps and such, and it's very easy for air to even escape from threading such here. So how we put on Teflon tape is we only want to put on a little bit. So basically we want to wrap the threading around about once or twice, nothing more. If you put too much, then it's not going to be a good fit anymore. And regardless of its name, Teflon tape isn't really a tape. It's not very sticky. The only way it'll stick to things is via static electricity. So I'm going to rip off a little part of the Teflon tape here. You can see this is a perfect length. And a really important part of applying Teflon tape onto threadings like this is that you want to put it on kind of clockwise. So you want to put it on the same way you would tighten this onto a different fitting. So we want to put it on this way, and you want to make sure that you have a good grip on it so that you can move it around. Just wrap it around as so. Another really important part is that you want to put the Teflon tape on the middle of the threading as much as you can. If you put it too far down, so it's sticking off of the threading, then there's a very high chance that it could get stuck somewhere in the system and create a clog of some sort. So it's just always safe to keep it like this. And if you put it too high up, if this was a longer threading, if you put it too high up, the Teflon tape won't make in contact with other fittings. So that's just not very helpful at all. So here, this is perfect Teflon tape. Move all that to the side. And so we're back to our T-fitting. That if we follow down, you see is connected to a gauge. This gauge, this is a pressure gauge right here. Not very good lighting, but it just shows us like how much pressure is in the system. And this is very important that stays on the storage pressure, so we can tell that this never goes above 120 psi. And also connected to it, I have this vent plug or vent valve, because if the pressure does get high, I want it to be very easy for me to just vent out all the pressure. And if you see here, when this handle is in line and parallel with the rest of the tubing, it means this valve is open, so air can easily escape out right now. And when it's perpendicular, such as this, it is now closed. So if for some reason your system isn't holding any air in, this is a very common reason for that. It's just you forgot to close the vent valve. As we follow here, we have two pressure tanks right here, air tanks. These are really important as well, because the more volume you have in your system, the kind of more air you can have, even though the pressure will seem to stay the same. Again, the more volume you have, the more air you have to use. So we follow it down here, just follow the tubing. We move it down over here, and we have it connected to a pressure regulator. And on this pressure regulator, as you can see here, maybe not because the lighting is not that good, but there's an arrow pointing out that way, which means there are 4 ports on the pressure regulator, and that means the one opposite from it is the one where there's no like the pressure is not getting regulated here. But every other port here, the 3 other ports, the pressure is going to be regulated to 60, which is why I stuck a pressure gauge right here on it, because this will read the working pressure. We also need to know the working pressure, because we only want the working pressure to be 60 psi. And out here, I have nothing connected to it right now, but we will have a solenoid connected later. So when we are putting together systems, we want to check first that the pressure regulator is calibrated to 60 psi, nothing more, nothing less. And of course, the way we adjust this is that you see this top part right here. We can pop this out, and then there's a little plus and minus on the top. You turn the knob closer to the plus, this will increase the pressure, or like increase the amount of pressure that's going to go to the working pressure side. And if you turn it towards the minus side, it will decrease the pressure. So we will check if the pressure is already this pressure regulator is already calibrated. Of course, we're going to make sure this vent valve is closed, and I'm going to turn on the circuit breaker. You can see, I don't know if you guys can hear it, but it's extremely loud right now. And you can see here in these many gauges, the pressure is now building up. We're at around 40 psi right now, and it's building up to 60. And now I want to move to here to make sure that it is 60. So right now it's exactly at 60, which is perfect. Now you guys can see it here. But to show you guys that we can move it up and down, there we are. If we turn it this way, you can see the pressure is moving down for the working pressure. And if we turn it the opposite way, it'll move back up. And we can move this past 60, but of course we don't want to. So we are going to save that right here. And just pop it back down. Now we'll stop the system. You can see the pressure relief valve actually just popped open because we went a little bit above 120. And now we will just vent. And a really important part of venting as well is you always want to call out when you're venting, because when we vent out all this air, it's going to be extremely loud, and we do not want that happening. And we don't want people to be scared. Not happening, but we don't want people to be scared and get jump scared by this. So we just want to yell out something like venting, and then let all the air out. All right. So that's what we have so far. And we know the pressure regulator works. So now it is safe to say that we can check out the cool pistons. I'm going to set this back up here. A little tilted. Perfect here. And I have two setups right now. I'm going to get safe. So I have two setups right here right now. I have a single solenoid, and then I have this single action piston. And you can see here with the single action piston, if I pull this out, it's going to be very tough to pull this out. Even if you guys can't see it, it's very tough to pull this out right now because there's a spring attached on it. And right when I let go of this piston, right when I let go of it, it's going to spring back in because there's a spring holding it. Opposed to, you can see here, a double piston or double action piston. Where you can see I can pull it out very easily, and then if I let go, it stays in position there. In order to move it back down, I have to push it down like that. So we're gonna connect this over here, and I'm gonna plug up these holes. So just, where'd my pressure regulator go? There you go. Let's take that out. And now I'm just going to connect this to the pressure regulator. Perfect. And you guys might be wondering how I'm going to be able to use this without programming. And it's actually very simple. There's a mechanical override on basically every single solenoid. And I don't know if you guys can see here, but basically the blue part right here, it can be used with this little screwdriver that I have. And if you twist it, it will activate the other port. If you twist it the opposite way, it'll switch to the other port. And it's also present on double solenoids. I'll show you guys that later. But here we are. A really important thing about using pistons is that you never want it pointed towards anyone. You never want it pointed towards anyone at all. I'm just going to turn this a little bit. You can see it very well. Make sure the area is clear. And now all we want to do is bring up the system again. Oh. So I had the pressure vent valve open. There you go. It's closed. Now we're closing the system again. And then we are building pressure again. So another really important thing about pistons is that when they are activated, it's going to jolt back because of conservation of energy. You can see right now the video is a little bit shaky, and that's because the compressor is shaking so much that it's shaking this entire table, including my camera. So it's going to be a little shaky for a bit, but hopefully you guys can tell that this right here is what's going to shoot out real quick. So I'm going to hold this down with both my arms here, and then once I activate this, you guys will see that it shoots out. So if I keep this activated here, it's just going to keep shooting out like that. But then if right when I twist this off, it'll slowly go back down. And the reason it shoots out so quickly, but it slows go back out, because it just takes some time to exhaust that air, and including with a spring, it's just a spring. It just makes it much slower to go out. And I'll just do that once again, right here. Shoots out, and then I can pull it back in. I can do that many times. All right, going to turn off the compressor, and then vent out all the air. Venting! Perfect, just like that. Now we're going to detach this part and then replace it with our double solenoid, or double piston / double solenoid build here. You can see here the same thing is present. The mechanical overrides, the same things are present on this double. You can see there are 2 of them instead of 1. That's because if I activate this one and then I turn it off, it will still, what's happening inside the double solenoid is that it's going to stay in the same position as it was. And the way to change positions to another one is to activate the other one and then turn it off again. And then you have to do that every single time you want to switch which way the piston is going. All right. Again, we always want this facing away. Plug it into the pressure regulator. And now I'm going to hold this down because the airways are open. I'm going to close it. And now we're going to start this up again once I close the vent valve, of course. I'm going to push everything back up on the table. And now we're going to turn on the compressor once again. And then watch the pressure go up a bit. And now we will activate this amazing double action piston. All right. So that was the wrong side. So we do right here. You see it shoots out like that. Once I activate it, and then once I close this port back up, you can see it just stays like that. I'm not touching anything. And once I open the other port, though, it will shoot back in. And you can see it's much faster than a single action piston. And the reason is because there's no spring, there's no home position in the solenoid. It's just much quicker, and you're shooting everything together. Perfect, just like that. Now we're going to turn this off. Vent out the air once again. Venting! And we're just going to disconnect this part from it and come back to our presentation. course, for safety purposes, we always want, whenever there's running, or whenever the compressor's running, whenever we're working with pneumatic components, we always want to have our hair up, and of course, our safety glasses on, because you never know what will go wrong. All right. So here we go to the more advanced components. So we've gone over kind of an overview of how to build the system. And now this is for a little more advanced stuff. So we've got check valves, we got quick exhaust valves, we have 3-position solenoids, manifolds, and flow control valves, which is something that we almost use every single year on the robot for our pneumatic stuff, because it's very, very helpful. And as it says there, it's utilizing the power for more than just a piston. We're going to start with the check valve, which only allows air to flow a singular direction. So we already have, so you can already kind of see that we have a check valve on the compressor. I don't know if you guys saw, but the first valve that comes out of the compressor is a check valve. And the reason we have that check valve is so pressure can't go back into the compressor and hurt it somehow and damage it. And this is actually essential for a 3-position solenoid, that it has a closed center. We'll go over what that means later, but it's essential for 3-position position solenoids with a closed center, because via FRC rules, we cannot with a closed center, if the piston is stuck in the closed center position when the robot is turned off, and then you open the vent plug, all of the air is not vented out of the system, because there's still pressurized air inside of the piston. So how we circumvent that is by using check valves. So we can basically connect this to, we can connect the outputs of the piston to the other outputs without the air coming in when we don't want it to. So when we open the vent plug, we let all the air out, including the air in the pistons. And with the check valve, it means that when our system is pressurized, the pistons won't also get pressurized, because without the check valve, that would happen. And then we have the quick exhaust valve, which is used to control the actuation speed of pneumatic cylinders. And as we've seen, generally the ones that I showed you guys, those were extremely small pistons, and typically we use bigger pistons, like the ones we used for climbing last year. It takes a lot more time for it to push out all the air so we can retract or extend. And the reason is because it has to travel through a lot of tubing in order to finally get back to the solenoid and exhaust there. So that's why we have these quick exhaust valves that we sometimes mount to the entryways, to the ends of our pistons. So when air is getting pushed out of the piston, it can be exhausted right there and right then. It's almost very similar to check valves, but they allow air in one way and they exhaust the air in instead of just blocking the air. The opposite one is going the opposite way. So these can make pistons actuate extremely fast, or they can even, or as slow as you can, with adjustable ones there. They're also inline ones, because the ones that are shown on the right, when you attach those to you have to attach those to the end of your pistons. So basically, instead of having these fittings at the end here, you'd have one of those. And those guys are quite a fair bit larger than the other fittings. So that's why if there's not enough space for it where you're mounting it, it's better to just have it in line and away from the cylinder. And then here we have 3-position solenoids. You can see as 3 positions opposed to only 2 positions. You can see the ones that showed they only had 2 positions. You could either exhaust air out one way or exhaust air out the other way. You can see with 3 positions, there's a center position, which can either be when both sides are activated at once, or if both sides are not activated. So it's like a home position, such as in a single solenoid. And there are just 3 different kinds that are most common, which is exhaust center, the pressure center, and block center. Exhaust meaning when it's in the center position, it will allow air and the pistons to come out from both sides. So both chambers of the piston, the air can be exhausted out. In the pressure center, it means both sides of the piston are being pressurized at once. Instead of only having one side pressurized at a time, pressure center allows both of them to be pressurized at once. And then block center is when it does not allow any air to go in or out of the piston. And we used this on our robot last year in order to be able to level on the hanging. And how we would do that is that whenever the piston is moving up and down, you can stop it anywhere in between rather than either at 100% extended or 100% retracted. So with a block center, if you were to make it, if it was, say the piston was entirely extended, and then you want it to come down a little bit. So you would activate the other side of the solenoid so it would start coming down, and right when it's at a position you want it to be, you can put it into block center so it will stay right where it is. It will not move at all. And that's how we would sometimes level a robot. If we wanted to level, we could shift our center of mass a little bit to the right or a little bit to the left, whatever is needed to equalize out the hanger.
All right, Natalie, pardon the interruption. I'm sorry to interrupt you, but we are running low on time. And I did want to get to a couple questions that I'm seeing in the chat. So a couple things I just wanted to, oh, perfect. Okay. So I just wanted to mention, I'm sorry to have to cut you short just by a few minutes. We will post the slideshow and also this video. So if anyone who is watching is interested in seeing, learning more about the manifolds, and then I missed your last slide, Natalie. So what was the last part that you were going to talk about?
It was about flow control valves.
Flow control. So if you'd like to learn about manifolds or flow control valves, there will be a little bit of a discussion, and then also the slides available to you. But we've got 3 questions that we'll have to fire through pretty quickly. So I'm going to just ask them real quick, if you don't mind giving just some brief answers to these questions before we transition to our next feed. So Nadim is asking about last year's robot and how much air we needed to store in our containers to be able to lift our robot for leveling. And then where did we buy those pistons? Do you remember the vendor?
It was from McMaster Car. So just McMaster, and we needed about 7 of these clippered air-powered tanks, basically. These tanks. We used 7 of them, and that was able to extend. So basically, bring our pistons entirely up, and then also bring us up and like retract it all the way twice. We just wanted that for extra stuff, just in case.
Perfect.
So, thanks for that. Yeah.
Cool, thank you. And then also we have a question from Cindy about how to troubleshoot non-working solenoids, and then also about double pistons extending unevenly. So how do you fix double pistons that extend unevenly? Do you have a suggestion for that?
So yeah, in flow control valves are actually perfect for that. That's what I was going to go over. If you notice that your pistons are firing unevenly, it's very easy to stick a flow control valve there, so you can adjust the airflow of how slow it moves up, how fast it moves up. You can control both sides with flow control valves.
All right, cool. So Cindy, what we'll do is we'll drop our email address in the chat, and if you'd like to reach out to our team, we'll forward that question to Natalie. She can get back to you about some specific answers on how to fix the pistons that are extending unevenly. We have another question from oh, I lost it here. Oh, it was from Cindy as well. But we're looking at if you wouldn't mind, Natalie, just describing what our climbing system did for last year. Like, how did it work? What were the main components of our system for climbing?
So we basically just had two really big double action pistons, and we had three position solenoids. So that would just basically allow it to move up and then move down and then stop it whichever way the close center is, I showed in one of the previous slides. And that's basically the entire gist of the system. All I had to do was extend all the way out, grab on, move all the way back down.
Awesome. Well, thank you so much, Natalie. This has been super informative and really, really awesome to listen to. Lots of information. We really appreciate it. So for now, if you would, we're just going to transition now to our last presentation for the day, which is our student-led team structure and leadership presented by Elizabeth and Sandra and William. Natalie, thank you again. And then to anyone who's listening, remember that you can reach out to us. I'll drop our email address in the chat. We are FRC Team 4645. And you can email any questions that you have, and we will get back to you with any questions. All right, we'll be back in just a few minutes, less than 10 minutes at 5 o'clock, excuse me. And we'll be back with Elizabeth, Sandra, and William. All right, everyone, welcome back to Stream 3. We are here with Sandra, Elizabeth, and William from Team 4645, and they're going to be chatting with you about how to run a bot dog stand. We're going to be diving into student-led leadership for team structure in terms of FRC. They have a lot of insight to give to you, and I'm excited to introduce to you our captains and our project manager from Team 4645, Chicago Style Bot Dogs.
Okay, hey everybody, welcome to our presentation, How to Run a Bot Dog Stand. This is about student-led team structure and leadership at our team 4645, the Chicago Style Bot Dogs. Today we're going to be talking a little bit about the leadership that we do as students at our team. I couldn't hear the stream, so I don't know exactly what Ms. Fetvick mentioned, but we really pride ourselves at 4645 on being like a student-led organization. And we do really appreciate our teachers, our coaches, and our friends in the industry. Shout out to Tim. But we really do, as students, have all of the control that we can, I think, over robotics. So we've learned a lot over the last 4 years, and we're hoping that we can kind of present to all of you some of our successes, some of not our failures, but some things that we've been able to improve on, and hopefully that can help inform what you do as a team, no matter what kind of team you run. So yeah, let's introduce ourselves. My name's Elizabeth. I'm one of the 2 team captains, and I've been on the team for 4 years. I used to be the leader of the electrical subsystem.
My name's William. I'm the other team captain. I've also been on the team for 4 years, and I used to be the leader of the mechanical subsystem.
Hello, I'm Sandra Hogan. I'm the project manager, and I've been on the Lane Tech's robotics team for 2 years. Next slide. Okay, so one of the most important necessities for running a successful team is team engagement. Our sub-teams work hard to teach our members valuable skills for robotics through informative and interactive lessons that are designed by our team's leads and second leads. Not only is it important to us that we teach our members, but that we're making sure that they're having fun and socializing as well. After all, we are just one big extended family. Next slide. Our media marketing sub-team begins every meeting with icebreakers instead of jumping straight into the lesson. It's important to us that we let our members know that they're in a safe place surrounded by people who care about all their accomplishments and challenges that they face on a daily basis. After icebreakers are over, the lesson begins. Whether we're discussing our team's social media, emailing sponsors, or practicing scouting, all of our lessons include interactive videos and slideshows that allow our members to actively follow along and visualize the lesson. We also allow our students to work in pairs to encourage social interactions and share ideas and knowledge. Remote learning has made it harder than normal to interact with one another and build friendships, but that has not stopped us from doing everything possible to allow our members to feel a part of the family. Lastly, we encourage our members to keep their videos on and verbally participate, because it allows us to become familiar with one another and engage in a more realistic and flowing conversation. Next slide, please. Our actuation pneumatics sub-team utilizes Peer Deck, Google Slides, questions, story-related lessons, drawing competitions, and lab bonding to extensively teach our members pneumatics. Our actuation pneumatics sub-team is obsessed with Peer Deck. It's very important to us that we allow our members to interact with the lesson. We have them draw and explain pneumatic components because we believe that repetition is key. The best way to reaffirm what was taught in the lesson is by having our students draw the components themselves. Google Slides is also very dear to our hearts because it allows us to not only present the lesson, but with editorial access, our students are able to answer questions and contribute. We also pause the lesson periodically to allow students time to ask questions if they need to. We work hard to provide our members with problems that are fun and interactive so they don't have to sit there and listen to long lessons that might end up boring them. They are asked to design pneumatic systems that accomplish goals such as blowing the snowman Big Snow's arm, which you can see on the right, back into his body using a pneumatic system, or explain how they can use pneumatics to close their bedroom doors when their parents leave it open. Next slide, please. In the 2019 to 2020 season, our mechanical sub-team relied heavily on in-person meetings to showcase to their members physical components in the lab and compare those materials with the CAD versions. In that season, they also studied the team's previous robots as well as robots from other teams to get a better understanding of the functionality of the robots and their components. This year, since we no longer have access to physical materials, mechanics relies heavily on tutorials to showcase the different materials. Especially when learning about CAD, visuals are so important to understanding the lesson. Thus, we use tons of tutorials to walk through each step. We also allow members to use tutorials to teach the group because teaching others helps them engage and learn the lesson. We also love utilizing breakout groups. It allows our members to work in groups to solve problems together. Networking is very important in robotics, so we encourage our members to exchange contact information or communicate on Slack to help each other solve problems. Google Projects allows for a variety of ideas to be shared and encourage collaboration, which is very important in robotics. We also end the meetings with group-friendly games because what better way to get more engagement than by playing games as a team? It allows for team building, encouraging competition and teamwork. Plus, who doesn't like to win? Next slide. Our fabrication group has worked on really fun projects this year, such as building a boat using only popsicle sticks, glue, rubber band, and other household items. They also have built their own CAD race cars. These interactive assignments allow our fabrication members to build their 3D software skills and get a feel for the type of building and creating projects they would do during a normal season. Our programming sub-team absolutely loves team building. This sub-team is a very tightly knit group because of how often they interact. Prior to the pandemic, they would often meet in person to go out to eat or meet up with each other to hang out. They talk daily in their group chats about numerous topics such as funny memes that they may have come across and, of course, programming. Through interacting so often, these sub-teams have become very comfortable with one another and collaborate wonderfully on their programming projects. These programming projects can also be fun, with many projects consisting of coding games that allow them to code to solve problems and create things. Next slide. Our team might usually seem to an outsider as all work, but we definitely love to play as well. When we aren't working in our sub-teams, we're branching out and having fun. From dancing together to inside jokes, our team continues to build the bonds and makes us a family. Next slide. Of course, one of the biggest factors that contribute to our team's engagement is through our competitions. Our entire team comes together to celebrate our hard work and dominate the field. We like to say that if you leave the competition with a voice, you weren't chanting loud enough. Next slide. We also love being able to converse with other teams, collect buttons, wear costumes, dance, sing, and have as much fun as possible with competition. Overall, team engagement is just one factor to running a successful Chicago-style bot dog stand. There you
go. So over the last years, we've tried a lot of different things to help our team, and a lot of it has definitely helped, and a lot of it has not so much helped, but it's still been a very big learning opportunity for us. So in 2018, our team was still relatively small, and we had our 4 FTC teams and our 1 main FRC team. And another big difference between 2018 to nowadays, we had what I like to call subsystems, where we were split into different groups pertaining to what part of the robot we worked on. So say intake, outtake, and manipulation or drivetrain. Each had their own individual leader, and nowadays it's more mechanical, just oversees all of that, and mechanical has its leader. Because of the such a small amount of people were on FRC and the main group, we had a very tight-knit community, and mentors were able to have one-on-one time with new rookies to really teach and explain to their best of ability what they're supposed to be learning. But sadly, we had less of an outreach on Lane Tech, and we just weren't as popular because it was a lot more selective, and we weren't as organized as we are today, which definitely brought up issues within the team. And this was the last year that we were called Ex Machina. So in 2019, our team blew up figuratively because of the success we found in 2018, and it became a lot more popular within Lane Tech. We also eliminated our 4 FTC teams and just decided to focus on FRC. And this was the first year with so many people, so we didn't really know what to do with all these people, and that definitely led to some issues with communication and some issues with one sub team having too many people and one sub team having not enough people. And so yeah. In 2020, our team just kept on growing, which was definitely great. Because of this, we were able to gain access to another room, and we also split up into satellite and core teams. Pretty much the core team is the team that had hands-on approach on the robot and was constantly changing what the robot did and how it worked. And the satellite team still had a very important role, but they didn't physically like work on the robot. So an example of this was we had a satellite team make a robot cart, which definitely is a necessity within FRC. It just doesn't have, it's not physically on the robot. We also, because of our growth, we decided to create a new leadership position called the second lead. And that kind of focused on newer members and catching them up to speed. And it was just really nice to have multiple people overseeing sometimes 20 or more people, which could definitely get chaotic. So this year, our team has obviously shrunk a little bit, sadly, but that's just natural because of COVID. And we've also had to modify how we teach online. As Sandra said in a previous slide, people have been using Pear Deck, and it's just a lot more, we're trying to interact a lot more because that's really the only way to tell if someone is learning. Where our COVID is a little bit beneficial because we're able to focus on sub-teams that have maybe fallen behind in the past and kind of boost up our skills in certain areas. We also like to take this time to kind of focus on the future of the team because it's important to leave behind a legacy, and we think that that's really the main way you grow. So we want to make sure everyone that comes after us is just as good, if not better, than us at their job. Members are not engaged this year just because naturally I feel personally, I don't like to kind of talk, especially when it's online. It's kind of, I get nervous, and I can see how a lot of other kids would feel the same way. So we like to interact and be friendly and just be like, hey, what do you think of this to people, and form good relationships that way. Another big issue we found was that we didn't have access to physical tools. And I know I personally am a very physical learner. So I really benefit from having something in my hands. And that was definitely a big issue when it came to teaching kids about, say, electronics, pneumatics, or CAD. There was nothing there to showcase what we were doing.
Yeah, so we've talked about student-led curriculums and outreach, and we've talked about some of the things we've tried in the past and where we are now. And I think we can all agree, at least within the team, that we're so much better off than we used to be. And part of that is owed partially to the tools that we've implemented to help bring people together and also stay organized. So next slide, please. So the first thing I want to talk a little bit about is Team Gantt. Actually, let me backtrack a little bit. As far as these tools go, I feel like I have to offer a disclaimer. Within the CPS system, teachers can't communicate with us outside of approved, like monitorable products. So this truly is something that we're managing independently as students. Sometimes our teachers will look at what we present to them to check in with it, but I just wanted to offer that as a disclaimer, just in case anyone from downtown is watching. Okay, so with that said, we have Team Gantt. Team Gantt is an online service that offers Gantt charts, which is a project management tool that works a lot like a calendar. You can put a task, for example, crimp wires. You tell the Gantt chart when that task starts, when it ends, and as you complete the task, you update it with a percentage that indicates how close it is to being done. It's a really simple system, but it's extremely useful because it provides a great representation of all the work that you've done and everything that you have left to do. So in this case, if somebody comes into the lab and maybe been sick for a few days and you gotta catch up, you can just take one look at the Gantt chart and you already know just by browsing through that what you need to do. If your hands are idle in the lab, you know where to look to go and find something to work on. Okay, next slide. The axis of the Gantt chart is maintained mostly by the first and second leads. So at the end of every day, the first and second leads will update the Gantt chart with new tasks. They'll update the progress of old tasks, and they'll arrange it as needed. Coaches do not have direct access to the Gantt chart, but debriefs are sometimes held, which we'll talk a little bit about on the next slide. As far as usage, team members, as I said, they can check the Gantt chart for next steps if their hands are idle. I think Will mentioned this, but in 2019, and a little bit last year too, but it was greatly alleviated by this system. Sometimes people didn't know what to do and they were too shy to ask, so they would kind of just like sit in the lab and, you know, they'd be just vibing there, which, you know, we prefer that everyone stays productive while they're in the lab. So you can just look at the Gantt chart and see like, oh, this person isn't done with this. I can work on this, and then go from there. It's also great visualizer. So on the next slide, please. You can see that there are a couple of different things that we use to help visualize tasks within the Gantt chart. One of them is dependencies. So on this window to the top left, you can see that a lot of Drew's tasks are changed together with gray lines. And what this means is the tasks that are farthest to the right, which means they're happening farther along in the calendar, are dependent on the tasks to the left. So if Drew needs to work on this project, he knows he needs to do he needs to do the tasks that have dependencies before he completes the others. This was kind of, I don't know if everyone else feels the same way, but I would assume so. This felt like a game changer for a lot of us, because I personally remember that in the past, people would have like an expectation of, so lots of things in a robot are very dependent on each other, and people would work on a mechanism and have the expectation that another piece would already be done. But then you'd walk over to that person and they'd be like, I haven't finished that. I'm still working on this, this, and this. And then you'd kind of be stuck in limbo and time would be lost as a result. So just being able to visualize exactly what has to come from what point really alleviated that. And I think we owe a lot to a good project management system to the success of our robot from last year. And then finally, this is a smaller thing, but task groups. You can easily sort tasks in Team Gantt, and we use those a lot. So we would create a category for each subsystem's tasks, but within that, we would also have smaller groups that met certain specifications. So for instance, in this box in the bottom right, you can see that we have something for before CIR. So on the electronics subteam, there were some things that we wanted to add and fix before the Central Illinois Regional, which did not happen, which is why some of those tasks are incomplete. But we had it right in front of us, you know, what we needed to do before a certain deadline, which was good. Okay, next slide. Okay, so the rules of Gantt. The reason I have this slide is because in 2019, we did have the Gantt chart, but we didn't use it well. And as a result, it was nowhere near as useful as it could have been. So between this year and last year, there are some things that changed, and I've consolidated those into the rules of Gantt. So hopefully by following these rules, you can implement this system just straight out of the gates and have a good time with it. So number one, Gantt has to be active to work. I talked already about how the sub-team leads updated it daily. That's really important, because if it's not up to date, it's kind of useless. So make sure you update it daily. Number two, every task starts with a verb. In 2019, when we started using this, sometimes people would input tasks and they would be kind of vague. Like, I don't know, arm completion. Like, let's just say you're building an arm and you know it needs to be finished by this date, so you make a task for it. That doesn't really work, because it doesn't really explain what you need to do to make that happen. It's just kind of a conception that, oh, this has to exist at this point. So a good rule of thumb is that if you start every task with a verb, it indicates a certain action. So if I say crimp wires, or cut Lexan. I know exactly what needs to be done, and it just helps you break it down in your mind into smaller steps. Number 3, everyone has to communicate for the chart to be truly powerful. So as nice as it is to have a cool online system that organizes things for you, and it's the internet. The internet is awesome, but it's nothing compared to just having a conversation with someone. So you have the chart, but you also got to make sure that as a student, you're going out of your way to talk to the person on the table next to you and make sure that everybody's on the same page. So it only goes so far. Number 4, weekly debriefs with the Gantt chart and sub-team leaders kept us on track during the early weeks. So I said I would talk about this later. During the early weeks of the season, the sub-team leaders would sit down with Miss Fetvick, and we would project the chart on the board, and we would just explain what we had done and what we were going to do next. And it was just a good system for accountability. Things got so hectic by the end that I don't think that we kept that up until the very end of the season, but at the beginning, it really was useful. So even though this is student-led stuff, it's okay to loop somebody in on it if you need to stay accountable. Be kept accountable. It's something that's difficult for teenagers, but we get it done. Okay, and then finally, color coding. This is just, a little silly thing, but Team Gantt supports color coding all the tasks, so we just picked a color for every task, and it just made it more visually recognizable. So that was good. All right, and then the second tool I'm going to talk about is Slack. So Slack, in essence, is an asynchronous chat client. You create a server that houses channels. Channels are specific areas for people to talk in. When we were trying to figure out how we wanted to communicate out of the classroom, we had a lot of options. At first, we were using GroupMe because it was an approved service by CPS, but that's no longer the case anymore. We weren't going to be talking to any adults through our chat service, so we just wanted to pick something that would be convenient for us, but also included the powerful tools that we needed. One thing we considered at first was using Discord, which is an extremely similar software, but we ultimately decided against it because Discord it's created for gaming and kind of like casual community. So we wanted to make sure that people could elect to keep their robotics kind of like stress and life separated from their personal life, and make sure that there was, even though we have fun on the Slack, that there is a certain level of, professionalism. Basically, we just wanted to make sure that you could be in the right headspace when you were hanging out on there. Okay, next slide. So I talked about channels. If you ever wanted to implement Slack on your own team, you could basically copy this structure. What we decided to do is that first we had general channels where people just talk about what's going on the team or in their lives or whatever. The two standard channels, the two standard channels generated by Slack are general and random. So in general, we just had that everybody could talk about their day at FRC or news from headquarters or anything like that. And in random, that was just any conversation about anything as long as it's appropriate. We also had fun posting, which was an opt-in channel for meme sharing. Really recommend that, because if you have people that like to post memes on your team, which I'm sure you do, it's good to have a dedicated spot for that, just so it doesn't overflow and kind of overtake other conversations. Okay, second, we had sub-team specific channels. In practice, we use these in more of a structured sense for like announcements for certain subsystems and posting links and so on and so forth, but we had a separate channel for each subsystem. And thirdly, we had channels for specific functions. So there's a rules channel. I think that's a pretty standard thing in most chat servers, but just so if a rookie logs in for the first time, they can see what the norms are. And second, we didn't use this that much, but we did have a channel specifically for file sharing. So early on, when we didn't have our Google Drive structure completely set up, if you had a file that you needed somebody else to download really fast, you could be like, oh, check the Slack, I dropped it in there, and then they would just download it really fast. So that's optional, but it could be useful depending on your situation. And then finally, you can create private channels in Slack. So we had one for the drive team. So during competition, we would be able to text each other and yell at each other to get to the pit when necessary. And for leadership and specific groups, you can have private channels for those. Okay, next slide. Some final specific components of Slack, I suppose. First, it is student moderated. So again, we're the only ones that touch this, but I thought it was worth saying that we haven't had any incidents at all, but if something were to happen, the expectation is that we would bring it to an adult or a coach. Again, we haven't had any problems, but it's good to have that plan in place. So if something makes you uncomfortable, students aren't the only ones that are in the loop on it. Second, one feature that is unique to Slack is threads. So in most chat clients, I would send a message, and then to reply to it, another person would just send a message after me. But to keep conversations organized, what you can do is reply specifically to a message and create a thread under it, and this is illustrated by the image on the right. So in this instance, I created a bulleted list of things, don't remember what it was, but it was a list, and then another kid on the team, Ethan, responded to that and asked a question. And it's kept in one spot, so if there's a compartmentalized discussion, it's there in one place, and it's easier to search through. We usually use that in sub-team channels. It's not necessary when you're just casually talking. And then finally, one of the fun features in Slack is statuses. So you can click a status to display next to your name, which is represented by an emoji. If you're an adult at work, you would use these for like, oh, I'm at the office, or I'm on vacation, or I'm out of town, message me later. But in our case, we decided to use them just so people could select an image that represents the subteam they're on. So at a glance, you can just tell, oh, this person's on electronics, this person's on fabrication. And our pride and joy, truly what technology has built to our whole lives. We have a Dean emoji. Definitely recommend that as well. Before we move on, one thing to mention is that Slack was purchased recently by Salesforce, and people have varying opinions on that, but I just wanted to mention that it was purchased and things might change, so who knows, maybe in 2 years none of this will apply, but I'm betting for the time being things are going to remain pretty stagnant, so for what it's worth. All right. So yeah, that's our presentation. We really blew through it pretty fast there, but we hope that was useful and kind of illustrates some of the things that I'm talking to you as if you were a student. You probably are. Some of the things that you can do to really take ownership of your team and make a difference for your peers. And I don't know, that's really powerful. Anyone else have thank yous to issue before we move on to Q&A?
No, you pretty much summed it up with that one.
All right. Well, thank you guys so much for doing this. This is wonderful to be part of. The student-led leader or student-led team structure is something that's been really important to our team for several years now, and it's cool to hear all of the ideas that came from like coaches come through you guys, and we're super excited. So. I actually haven't had any questions come through on the YouTube live chat. So I have a couple questions for you guys, if you don't mind me putting you on the spot for a moment. And of course, I'll give you some time to think about it. But we'll just go, if you don't mind, in alphabetical order the way that I see you on my screen here. So Elizabeth, and then Sandra, and then William. I just want you to share a memory that you have of FRC and why this program is important to you. So obviously something that we're all missing and disappointed about for this season being adjusted the way that it has to be due to the pandemic. I want to share some good memories about why this program is important, why students should be involved, and why they should be a part of a team. So Elizabeth, why don't you share a memory that you have of FRC?
Okay, so isolating a specific memory is just impossible, but I think when I joined FRC my freshman year, I started off on one of the old FTC teams, and then I was kind of brought into FRC, and I was so anxious. Like, I know sometimes people say that, and it's possible to overcome it. But at the time, I was so anxious to the extent I was so excited to be on FRC, and I was so excited to be with the people that were there because I really respected them and looked up to them. But I couldn't bring myself to speak like more than a couple of sentences every day, which frustrated me. I remember my dad picked me up once, and he was like, "So how was it?" And I was like, "I, I, I like said one thing all day, and it was crazy, you know." But because of the community that was created in our team and at FRC, like I already knew I wanted to be on robotics. Like this was really my dream going to high school, but because of the people that were there and the community that FRC created, I was able to overcome that. And at the time, that wasn't really something that I anticipated. And hey, now I'm team captain, so it all worked out. Anyway, this is, I guess the point is like this program, FRC is really something else. Like we're really lucky to be here. I certainly am.
To go off with Elizabeth says, like, so I was on the other spectrum. Like, I'm someone who's like really outgoing. I love socializing, and so to be a part of the robotics team, which is amazing to me. As William had talked about one time, it's like we were put into like sub teams, right? So I was originally a part of the electronic sub team, and then I kind of branched my way out because I don't like really to be like confined to one group. So I was always like in every single group. One day I'd be checking in on programming and just spending the entire day talking with them and learning about what they're doing. The next day I'm working with mechanical and see how they're working on the robot. So I just love socializing, and especially like being able to come in on Saturdays. And just spend the entire Saturday working not only on the robot but building friendships. It was just so valuable to me. So it was definitely like worthwhile.
Yeah, so I have more or less two things. My first one, back when I was a sophomore, um, I worked on something called the ARM, which sadly never really worked. Um, and so that was a really big disappointment. And the year later, I worked on something I like to call the indexer, and I remember that time that it first worked, and just the pure rush of joy and happiness that I felt. That's why I'm on the robotics team. Just it's amazing when you do something and you're proud of it. There's nothing better than that. And then my second thing, so I have kind of two main friend groups that I hang out with a lot. One of them's a robotics friend group because I love robotics, and another one's kind of a separated friend group. But I even my separated friend group I've met through people at robotics. So it's like all of my friends and my social skills and my social life stems back to robotics. And if I didn't join robotics, I just wouldn't be the same person I am today. And it's amazing to me.
Thank you guys for sharing. It's really special to be able to know who you were like when you first came to the program and to see how you've grown since you've become leaders in the program. And Wilbert, you spoke about feeling that rush of adrenaline when you have something that you and your teammates built personally have like work the way that you expected it to. And I'm wondering, like, as leaders now in the group for our team, how does it feel to be able to see the success of your team grow as well? So similar to what you were saying about how you were able to like see the product that you built work the way that you wanted it to. How does it happen on the other side of like the human part of the team? What does it feel like to be a leader and to see your team be successful and to see your teammates grow and to see your team just mature in a way that you had a direct part of?
I guess I'll go first. Um, I mean, I think for a lot of us, that experience kind of parallels like how we've grown as people. So we've already talked a little bit about that, but um, just I don't like how do you? Okay, let me try something else. Growing alongside a program is more than just like seeing a number. increase. Like maybe you don't notice in the moment, but having the opportunity to grow with people and see other people benefit, like also partially because of what you've been able to, like being able to contribute something to something that also made you a better person it's great. It's a good thing.
Okay, so let's see if I still remember the question. Um, so this was only my second year on the team. Last year was my first year. I came in as a rookie, and I came in with absolutely no experience. Like I wanted to join the team as a freshman, but through personal challenges, I wasn't able to join my freshman year. So my junior year, I came back and I was like, okay, I'm dedicated. I'm gonna join. This is something I want to do. Something I want to pursue like later on. So I joined the team, and I had no background experience. I came in with a few other rookies who some people had experience working on similar projects. Some people came in with experience of working on robots. Some people came in with they just had like family who like did something close to it. I had nothing tying me to robotics besides like a passion for it. So I feel like I really grew, and it's like having people. Well, we have like veterans who like work directly with the rookies and help the rookies learn and grow. So working directly with so many veterans has helped me learn so much. And there's things that I can tell you about that I wouldn't know last year. Like there's just so much I've learned. I feel like it really has changed me as a person, and it's set me up better for the position that I want to be in when I start pursuing this as an actual passion.
Yeah, I think also there's an aspect to learning within robotics that you don't get if you just teach yourself. Like if I were to teach myself how to CAD, I'd be like, cool, I'm 90% through this tutorial. That's awesome. But when I was learning in sophomore year, I was learning alongside other people, and I genuinely was happy for when they were found out how to do something that they were stuck on. And it was just a bond that is so personal and so just enjoyable that it's really amazing. And just seeing other people grow alongside what you're doing and just helping other people grow is honestly one of the main pillars of FRC, in my opinion.
Thank you for sharing, guys. We've got a couple questions here coming through the chat. So Nadim is asking about how we deal with teaching the different sub teams. So, for example, how often do you meet? How long? And what material do you cover? So, can you talk a little bit about the team structure in terms of sub teams and how those sub teams teach one another and propagate that knowledge from one year to the next, and then also how each sub team interacts with one another, and possibly also how the core team ties into sub teams.
I can kind of get started on that one.
Yes, Sandra, you go. We unmuted it exactly.
I'll get a little started, and Elizabeth can probably follow up if there's anything I don't address. So for as of this year, what we're doing with sub teams is the sub team leads. So we have leads and second leads. Our sub team leads and our second leads kind of design a lesson plan, and we all have this in one it's almost like a chart kind of thing. So everything is laid out for every single week with the materials they're going to be using, the lessons that they want to bring in, things like that. So everything's put into one space, and everyone's able to look at it and say, okay, for the next week we're going to be working on CADing. The week after, let's say for media marketing, we're working on fixing our website. So everything's put into one spot. And we also make sure to constantly communicate with our students. So like Elizabeth had mentioned beforehand, we use Slack, but we also have we send out emails periodically to say, hey, make sure you guys are prepared for this. We're going to be doing this. Another thing is we all to address the question of like how often do we meet. For sub teams, we meet once a week. So like we have 3 sub teams I think that meet on Mondays. We have I believe like 2 on a Tuesday. I think it's 1 or 2 on a Wednesday, and then one on a things like that. I don't remember. But it's like we have them only meet once a week, just so it's better for everyone else. There's not too much stress put on the captains, our leads, and our coaches. So we kind of like branch it out, but we still meet pretty often. We still keep in touch, so we give them projects to do even when we aren't inside of the actual meeting.
Yeah. So to elaborate, I think it's important to mention that most of our teaching, like when we figure out how we're going to bring the next freshman up to speed on this stuff, we do this starting in October. So before the season starts, that's when we're doing all of our introductory stuff. And then the hope is that by the time we get to kickoff, come the new year, everyone's just ready to go, and you can just let everyone get to work with the first lead kind of navigating and guiding the core team, and the second lead guiding the satellite teams towards whatever they're trying to accomplish. Did we talk about scheduling? I don't know. But during the build season, we meet every day until I don't remember what time. Can someone else talk about scheduling? Because, like, for whatever reason, I can never remember the specific.
Yeah. So scheduling during the season, it's every day until I think around 6 usually. Sometimes we get earlier, around 5:30 or so. And then depending on if the coaches are able to make it, we sometimes do Saturdays also, from I think around 11 to 3. So it's definitely not an easy 8 weeks right after winter break, but before winter break, it's once a week, so it's not that big of a deal. You can just go and learn some new cool stuff, and then, spend 8 weeks every single day after winter break.
Thank you for sharing, guys. So one question we have from Lockport Porterbots, they want to know how we select our team leadership, and they're curious to know how we avoid popularity contests and how we find students who will be accountable. So I'm going to let you guys answer that question first, and if I need to elaborate, I might jump in.
Okay, so for the first lead, so like the head of every sub team, well, I guess it's kind of built up over the years. So before me, there was Ghost was the electronics sub team leader before me. And then I worked really hard and I put in a lot of effort. And I believe Ghost told our coaches that I would be a good representative to be the first lead of electronics. So, and then I became the first lead of electronics, and I trained a bunch of new people, and then a lot of those people worked really hard, and I was able to see that Cassie was a really hard worker. So Ghost and I told our coaches that Cassie would be a great person to be second lead, so she became second lead. We don't vote, or I don't make a decision on who fills which role, but I think our coaches take our advice into consideration, and then they also see from a distance who's motivated and serious about the program. So I think, yeah, I think over time it tends to work out.
Yeah, so going off a little bit on that, it's also kind of like an honor system where if I were to just nominate my friend, then come on, everyone would be able to tell that it was my friend and there was clearly someone better for the position. And then I would just look foolish. So it's just kind of, I also just want the best for the future of the team. So why wouldn't I just nominate who I think is the best person for that job?
Yeah, thank you guys so much for sharing. So to anyone who's listening, real quick, I just wanted to introduce myself. My name is Lindsay. I am the head coach of the Team 4645, the Chicago Style Bot Dogs. I'm one of 5 coaches actually for our team, and each of our coaches oversee one of or multiple of the 6 sub teams that we have. And like Elizabeth was mentioning, through observation, through years of getting to know students, we choose our student leadership as a panel of coaches. Something that was mentioned in the presentation is that the way that our team is structured is we have our students divided based on their interests into 6 sub-teams throughout the entire school year. And then during build season, it's actually our student leaders who nominate individual team members to be part of our core team. And core stands for Competition Robot Engineers Team. And so those are the students who have, like Wilbert was mentioning, the hands-on experience of building the robot, meeting every single day until 7 p.m., building our robot. So we kind of have this tiered approach to building our student leadership. And the student leadership board this year is 15 student members. We have 3 top leaders, 2 captains and project managers. So Elizabeth and William are our captains. Sandra is our project manager. Each one of these individuals is assigned 1 of or 2 of the 6 sub teams that exist in our team, and then they are kind of like the avenue or the route where all issues kind of reach the coaches. So it's a very student, like Elizabeth had mentioned, it's a very student driven program. I see in the chat that you had asked about sharing some lesson plans, and of course we will absolutely do that. I'm going to drop our email address in the chat, and feel free to reach out to us, and we would love to share anything that we can with you. One last question that I have for you guys, well, it's not me, sorry, it's from Alp. Alp is asking about how Team 4645 looks to balance community versus competition. So how do we balance the community aspect of robotics versus the competitive aspect of robotics?
We've talked a little bit already about how during the off season we try to bring people together as friends as well as teammates, but I think part of it is also mindset. So I think maybe someone else can speak to this, but when we're in the lab working together, we know we want to succeed in competition, but I think everyone's thinking about doing their work just as best as they can, and encouraging an environment where people are working together to get that to happen, I think really like makes community the thing that makes competition possible. Maybe that makes sense.
Yeah, I'd say that makes sense. We also, outside of robotics, we like to have community events. So, say, for an example, last year, towards winter break, um, I got to set up like a little bowling event where the mechanical sub team went bowling. It was really fun. We bowled for a couple hours. Definitely strengthened a lot of relationships, and it was a great event.
To go off of that and not only address with like what's happening inside of our team but also other teams as well when it comes to competition, I know last year we did this thing where we hosted like a meeting where all these other teams could come and meet with us, and it was just like robotics teams working on like one set, and we got to like introduce ourselves and have fun. And I think just the spirit of FRC is just like getting to know one each other. Like, yeah, it's competition when it comes onto the field, but off the field we have stands and we have like buttons and things like that, and we're able to interact and like actually know them on a personal level and not just someone like we're competing against.
Thank you guys so much for sharing everything that you know about our team structure and how we incorporate student voices into our team leadership, into our just the way that our team operates. I appreciate all of the information that you've shared, and I'm sure that the viewers do as well. We actually are going to take a brief break before we have our closing statements from the organizers of the 2020 CRA Conference. Thank you guys again, Elizabeth, Sandra, and William, for sharing all that you know about team structure. I'm going to transition to our wait screen, and we'll be back at 6 p.m. with our closing statements. Thank you.
we're live on all the streams. Well, thank you guys, everyone, for joining us today. Sincerely appreciate you guys attending the 2020 CRA Conference. I have this feedback form that I'd really appreciate if you guys fill out for us. It is just a bit.ly link /2020 CRA Conference feedback, and you've got to use the capital letters where it seems correct. This will also come out in an email to all of the mentors. So if you guys have an opportunity, please fill out the feedback. I want to thank all of our presenters for sharing their knowledge. I think without them, obviously, this would not have been possible. And so they're a big part of making this possible. Besides that, there's a few people I really need to thank who are behind the scenes. We have a conference committee. So Nick from 1781 Electric Eagles, Mike also from 1781, Lindsay from 4645, and Darren from 8096. As well as myself, we're all part of this committee, and they're a huge help. Also, shout out to Paul, who's also a mentor from 1781, who was managing one of the streams today. These guys have been working on this for the past few months, I think almost all the way till September, or maybe even before. We've been going back and forth on emails and getting this together. So really appreciate all of you guys so much. I hope you know that. And I'll tell you guys later too. And then the last thing I have is if mentors, you want to get in touch with other teams or receive emails from other teams and you're okay with that, we've created this Google Groups that you can sign up for, put your email address down, and that way you can send and receive teams to all other Illinois FRC teams. That is all I have. Nick, Mike, if you guys want to add anything.
I just wanted to say big shout out to Shaman and Hawks on the Horizon for the coordination that they did, because we hosted this in person before, and we were like, well, I don't know, and then Shaman was like, guess what I did? I signed everybody up to do this thing, like, sent out email, everybody's showing up, and really big thanks to Shaman for making sure to negotiate and honestly sucker everybody into doing this. No, it was worth it though. I was telling the other mentors that I'm so proud of all the students. Such amazing work that you all are doing, and yeah, it makes me feel better about the world. And yeah, so thank you to all the teams. Thank you, for all the help from the other mentors beyond Chicago for helping us out. Really cool. We appreciate it. And yeah, thank you to all of you.
Yes, I also want to thank Shravan for ringing us in to this to make it our second annual happen. This was actually inspiring. It was great to see a number of familiar faces and also see all the students also with their great presentations. It was just great. Just can't wait till we can get back. Well, we still are helping each other out, which is great. And just when we are able to see each other in person, it'll be even better. So, thanks again, everyone.
Great. Well, with that, you guys can stay tuned. We'll have a kickoff thing coming in January, hopefully. But if you ever want to get the community together, let's figure out a way. That's the whole point of this. So, keep roboting on. I don't have any cool sign off, but something like that.
Rock on!
Rock on. All right. Thank you, guys. Thank you, everybody.